Hey guys, good morning and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats with some fire emojis. Everyone. Am I perfectly audible, visible? Yes, let me know in the chats. Am I perfectly audible, visible to everyone? Welcome back, guys. Welcome back. Welcome back and very good morning. Let me know quickly in the chats. Perfect, perfect, perfect. Amazing. Amazing, guys. Amazing. So people, as you all must be knowing, today we are going to do a mega marathon of your class 11th physical chemistry, right? A mega marathon of your class 11th physical chemistry. The chapters that we shall be covering in the today's session is going to be your mole concept, atomic structure, redox reactions, chemical equilibrium, ionic equilibrium, as well as thermodynamics, right? So this forms your class 11th physical chemistry, which is, I would say 50%, or not 50%, I would say it is 60% of your class 11th chemistry, basically, which we are going to discuss in the today's session, right? And you already know, my dear students, from the mole concept in your NEET examination, you get 2 questions. From your redox reaction also, you get 1 to 2 questions. From your atomic structure, 2 questions. Equilibrium, 3 to 4 questions. And your thermodynamics also 3 to 4 questions. Now you can understand how many marks you guys are going to fetch from this particular session. I just want you guys to be with me till the end, because the session duration is going to be long. It will not take less than 12 hours to complete this entire session. So I would want you guys to be with me till the end, right? Are you guys ready for that? Just tell me that. Are you ready for that? Yeah? Just tell me that, people. Just tell me that. And one question I would want to ask you before starting. Can you let me know from which part of the country you guys are watching this live right now? I just want to see. Which state? Which part of the country you guys are watching this session from right now? I would want you guys to write your states in the chats. Let me see from where the majority is. Let me see from where the majority is. All right. Amazing, amazing. So majority is from South India. That's great. South India's most trusted channel, this Unacademy NEET English is. That's something which I already know. This is something which I already expected. Perfect, perfect, perfect. Amazing, guys. Oh, there are some people watching from Kashmir as well. That's great. That's great. That's great. Perfect, people. Perfect. So, are you all ready? Should we start the session then? Let me just have some water first. Yeah? Let me just have water first, and then we shall be starting. And guys, one thing I would want in this particular session, I would want you guys to make short notes with me. Whatever things I'll be writing on the screen, do not note down every single thing. Just take important points. Whatever things I'll be writing, just take important points from them. Okay, and make short notes. Okay, make short notes for sure. Do not miss that. Because those short notes are going to be effective when you'll be doing the revision again of these 5 to 6 chapters of your class 11th chemistry. Okay, and one thing I'll make sure that whatever problem patterns can be asked, whatever questions can be asked from these chapters, I'll try to show you all those sort of questions which can be asked in your upcoming NEET 2025 examination. Perfect. All right. So let's get going then. Let's get started with the first chapter, my dear students. With the first chapter, which we shall be covering, that is your chapter number 1 of your class 11th physical chemistry, which is the mole concept. So we shall be covering the mole concept first. Okay? We shall be covering the mole concept chapter first. All right. So let's get going with the first chapter of your class 11th physical. That is your epic mole concept. That is your epic mole concept. Just give me a second. Let me fix certain things first. All right. The epic mole concept. My dear students, before starting this particular chapter, I'm going to let you know about a very simple terminology which I shall be frequently using in this chapter. What is that terminology which you must remember? I would say that terminology is your AMU, atomic mass unit. This AMU is also what you call it as U as well, or you can call it as D as well. First of all, the AMU term, as I have mentioned over here, let me tell you, it stands for the atomic mass unit. This term U, which I have mentioned over here, let me tell you, it stands for the unified mass. And this D over here, it stands for the Dalton. So the first terminology that I shall be discussing with you, that is going to be AMU, also called as U, also called as D. Now, my dear students, what this AMU exactly is all about. What this AMU exactly is all about. Try to understand. My dear students, this AMU, it is defined as 1/12 of the mass of carbon-12 atom. It is defined as 1/12. It is defined as 1/12 of what? It is defined as 1/12 of the mass of carbon-12 atom. Let me tell you, the mass of carbon-12 atom. The mass of carbon-12 atom, you must be knowing, the mass of one entire carbon-12 atom is nothing but 1.99 into 10 raised power minus 23 grams. And this mass of carbon-12 atom was calculated by the technique called as mass spectrometry. The mass of one carbon-12 atom, which was found out to be 1.99 into 10 raised power minus 23 grams. It was found out to be by means of a technique called as mass spectrometry. Now, my dear students, if you know the mass of one carbon-12 atom, which comes out to be this much, if you divide this particular number by 12, what do I mean? If I divide 1.99 into 10 raised power minus 23 grams by the number 12, what do we exactly get? We get the value 1.66 into 10 raised power minus 24 grams. We get the value exactly as 1.66 into 10 raised power minus 24 grams. Now, people, if I ask you, what is this particular stuff? What is this particular thing? Number one. And what is this particular thing? Are they same or different? See, this 1.99 into 10 raised power minus 23 grams, it is the mass of the entire carbon-12 atom. And this particular term, 1.66 into 10 raised power minus 24 grams, it is the mass of 1/12 of the carbon-12 atom. It is the mass of 1/12 of the carbon-12 atom. I believe this is clear to everyone. At the same time, this particular term, 1.66 into 10 raised power minus 24 grams, I can further write it as 1 divided by Avogadro's number. I can further write it as 1 divided by Avogadro's number. My dear students, you can check it out when 1 is divided with the Avogadro's number. When 1 is divided with the number 6.022 into 10 raised power 23, when you divide 1 with that particular number, what do we exactly get? We exactly get 1.66 into 10 raised power minus 24. So sometimes I'll be writing the exact value 1.66 into 10 raised power minus 24, or sometimes instead of this particular value, I'll be writing 1 divided by Avogadro's number. So my dear students, the first term. My dear students, the first term. What is that? That is atomic mass unit, which is also what you call as unified mass, which is also what you call as the Dalton, and defined as 1/12 of the mass of carbon-12 atom, whose value exactly comes out to be 1.66 into 10 raised power minus 24 grams, or in short, you can write it as 1 divided by Avogadro's number. Am I clear with this? Say yes or no in the chats quickly. Say yes or no in the chats quickly, people. Say yes or no in the chats quickly. Perfect. Amazing. Now, my dear students, this atomic mass unit, this AMU, let me tell you, it is kept as a standard. It is kept as a standard, or I would say it is kept as a reference. It is kept as a reference. It is kept as a reference. What is meant by that? See, from now onwards, whenever we are supposed to calculate mass of some atom, from now onwards, whenever we are supposed to calculate the mass of an atom, whenever we are supposed to calculate the mass of the molecule, we will be calculating mass of atoms, mass of molecules with respect to this atomic mass unit. So this is going to be our reference. This is going to be our reference. This is going to be our standard with which we shall be comparing the masses of different atoms or molecules. This is going to be the reference. This is going to be the standard with which I shall be comparing the masses of different atoms or molecules. For example, have a look. Have a look, people. For example, let me write a term over here as one of the basic term. Let me write the term over here as atomic mass. Everyone would have come across this particular term in their lives, I'm sure. Atomic mass. How do we define the term atomic mass, first of all? My dear students, it's a very simple thing. Atomic mass, in short terminologies, it is defined as the mass of single atom of an element. It is defined as the mass of single atom of an element. For example, let's say I'm asking you what is the atomic mass of oxygen. Let's say I'm asking you what is the atomic mass of oxygen. What does that mean? That means I'm asking you to calculate the mass of one atom of oxygen. For example, I'm asking you to calculate the atomic mass of nitrogen. What does that mean? That means I'm asking you to calculate the mass of one atom of nitrogen. For example, I'm asking you to calculate the atomic mass of sodium. That means I'm asking you to calculate the mass of one atom of sodium, in short. So basically, atomic mass is nothing. It is defined as the mass of one atom of an element, the mass of single atom of an element. I believe this is clear. And if this is clear, my dear students, let me write one simple statement over here. Have a look. For example, I'm writing a term, atomic mass of oxygen. Atomic mass of oxygen. First of all, what does it mean? Atomic mass of oxygen, what does it mean? It means that I am talking about the mass of one atom of oxygen. And all of you must be knowing the mass of one atom of oxygen. That is the atomic mass of oxygen. Is nothing but, that is 16 AMU. That is 16 AMU. Now, my dear students, What is the meaning of the 16 AMU? In order to understand its meaning, let me break the 16 AMU as 16 multiplied by 1 AMU. I can do that, right? Instead of 16 AMU, I wrote 16 multiplied by 1 AMU. Does not make a difference. Or let me tell you, instead of this 1 AMU, I can write 1 by 12th of the mass of carbon-12 atom. Can be written. Instead of 1 AMU, I'm just writing 1/12th of the mass of carbon-12 atom. My dear students, instead of 1 AMU, I can also write 1.66 into 10 raised power minus 24 grams. I can do that. Instead of the same 1 AMU, I can write 1 divided by Avogadro's number, and I'll keep the units in grams. Right? Now try to understand the meaning of all these terms. Understand carefully. I'm writing the term atomic mass of oxygen. That means I'm talking about the mass of one atom of oxygen, right? And mass of one atom of oxygen came out to be how much? It came out to be 16 AMU. What does it mean? It means that one atom of oxygen is 16 times heavier than what? One atom of oxygen is 16 times heavier than 1 AMU, right? Or I can say one atom of oxygen is 16 times heavier than 1/12th of the mass of carbon-12 atom, right? It is 16 times heavier than 1/12th of mass of carbon-12 atom. Or my dear students, I can say this particular term, it is the mass of one oxygen atom in what? It is the mass of one oxygen atom in grams. It is a mass of one oxygen atom in grams. Even this particular term, it is also the mass of one oxygen atom in grams. I believe this is clear. I wrote a term atomic mass of oxygen, 16 AMU. That means one atom of oxygen is 16 times heavier than 1 AMU. 16 times heavier than 1/12th of mass of carbon-12 atom. This is the mass of one oxygen atom in grams. Even this is the mass of one oxygen atom in grams. Right? So I would say, in short, atomic mass is a number. Atomic mass is a number which gives an idea. Atomic mass is a number which gives an idea about how many times an atom of an element is heavier than 1 AMU. Is heavier than 1 AMU. Quickly in the chats if this is clear. Everyone in the chats. Perfect, guys. Amazing. Now, let me tell you a few more things which I would want you guys to remember from now onwards. What are those basic things? My dear students, for example, I'm writing a term sodium over here. This is sodium. It's the symbol of sodium, Na, right? This is not Avogadro's number, okay? This is sodium. First of all, for sodium, I'm going to write few terminologies. The first terminology I'm writing as 23 AMU. Second terminology, I'm just writing 23. Third terminology, I'm writing 23 multiplied by 1.66 into 10 raised power minus 24 grams. These are the three terminologies which I have specified. Which I have specified for what? Which I have mentioned for the sodium. Now people, try to understand. This 23 AMU, I would be simply calling it as the atomic mass of sodium. I would be calling it as the mass of one atom of sodium in what? In AMU. This 23 only, without the units. Only 23, without the units. This is something which you will be calling as the relative atomic mass of sodium. This is what you will be calling as the relative atomic mass of sodium. And this particular term, this entire term, you will be calling it as the actual mass of sodium. You will be calling it as the actual mass of sodium, right? So these are the three terms which you need to remember from now on. Okay, perfect. Take a note of one important thing. Take a note of one important thing. Take a note of one important thing. On changing the scale, what is the scale which we have chosen? We have chosen 1 AMU as 1/12 of the mass of carbon to an atom. We have chosen 1 AMU as 1/12 of the mass of carbon to an atom. Now we can change the scale as well. Let 1 AMU be 1/6 of mass of carbon to an atom. Let 1 AMU be 1/24 of the mass of carbon to an atom. Right? So we can change the scale. Remember, on changing the scale, actual mass of the substance, does not change. Remember this particular statement? It can be asked because you would have seen from the last 3-4 years, a lot of statement-based questions are asked, and this is one of the statement-based question which can be asked. On changing the scale, actual mass of the substance does not change at all. I believe the term atomic mass is clear to you. And if the term atomic mass is clear to you, then you should be giving the answer of this particular question. One simple question I'm giving you. Try to answer this question. I'm writing a question. Calculate the mass of 10 nitrogen atoms. Calculate the mass of 10 nitrogen atoms in AMU in grams. A simple and basic question. First of all, we have to calculate the mass of 10 nitrogen atoms. Let me first of all talk about one nitrogen atom. Mass of one nitrogen atom is equal to, in AMU is equal to 14 AMU. In grams is equal to 14 multiplied by 1.66 into 10 raised power minus 24 grams. Right? This is the mass of one nitrogen atom in AMU. This is the mass of one nitrogen atom in grams. But am I supposed to calculate the mass of one nitrogen atom or 10? I'm supposed to calculate the mass of 10, right? So what would be the mass of 10 nitrogen atoms? I would say the mass of 10 nitrogen atoms would be 140 AMU. And it's going to be 140 multiplied by 1.66 into 10 raised power minus 24 grams. Right, people? So this is the mass of 10 nitrogen atoms in AMU. This is the mass of 10 nitrogen atoms in grams. Or you could have given the answer in terms of Na as well. You could have written it as 140 multiplied by 1 by Avogadro's number. This can be one more probable answer as well. Because you know 1.66 into 10 raised power minus 24. It is mentioned as 1 by Avogadro's number. Is this clear, people? Is this clear? Everyone in the chats quickly. Is this clear? Everyone in the chats quickly. The second term is your, one more basic term you must have heard, that is your molecular mass. Now, people, how do you define this particular stuff? What is your molecular mass? How do you define it? How do you define it? It is defined as the mass of single molecule. By the way, I'm not writing the definitions in detail. I'm just writing the crux of the definitions. I'm writing that stuff only which you have to remember, which will be used in your examination, right? Okay. See, molecular mass is nothing but it is defined as the mass of single molecule. It is defined as the mass of single molecule. Or, my dear students, how do you calculate this molecular mass? It is defined as the sum of atomic masses of all the elements. It is defined as the sum of atomic masses. It is defined as the sum of atomic masses of all the elements present in a molecule. For example, have a look. Let's say I have got ozone, O3. Let's say I've got ozone, O3. For example, I want to calculate molecular mass of this O3. Let's say I want to calculate molecular mass of this O3. What does that mean? That means I want to calculate the mass of one molecule of ozone. That means I want to calculate the mass of one molecule of ozone. And how do I calculate it? Sum of atomic masses, right? In ozone, there is only one element, oxygen. What is the atomic mass of oxygen? 16 AMU. How many oxygen atoms do we have? 3 oxygen atoms. The value comes out to be 48. Now you can either write AMU, or you can write U, or you can write D. Choice is all yours. Okay? But preferably, in case of molecules, we use the term U. Preferably, in case of molecules, we use the term U. Now, people, rest of the things you can do on your own. You can break this 48U as 48 multiplied by 1U. Or instead of 1U, you can write 1.66 into 10 raised power minus 24 grams. Instead of 1U, you can write 1 divided by Avogadro's number in grams. Right? Tell me the meaning of all this stuff. Tell me the meaning of all this stuff, people. Tell me the meaning of all this stuff. So basically, I'm talking about the molecular mass of ozone, right? Which came out to be 48U. It means that one molecule of ozone is 48 times heavier than 1U, right? One molecule of ozone is 48 times heavier than 1U. Or I would say, this is the mass of one ozone molecule in grams, right? Even this is the mass of one ozone molecule in grams. I believe this is clear to everyone, right? Similarly, people, similarly, let's say I'm taking ammonia, NH3. I want to calculate the molecular mass of ammonia. Molecular mass of ammonia. That means I want to calculate the mass of one molecule of ammonia. How do you do it? Sum of atomic masses. Start with nitrogen. Atomic mass of nitrogen is 14 AMU. One nitrogen atom. Atomic mass of hydrogen is 1 AMU. 3 nitrogen atoms. The value comes out to be 17U. Right? You can write it as 17 multiplied by 1U. Or instead of 1U, you can write 1/12 of the mass of carbon-12 atom. Instead of 1U, you can write 1.66 into 10 raised power minus 24 grams. Or instead of 1U, you can write 1 divided by Avogadro's number in grams. Anything you can write. Okay? Now you should know the meaning of all this stuff. I'm talking about the molecular mass of ammonia, which came out to be 17U. One molecule of ammonia is 17 times heavier than 1U. One molecule of ammonia is 17 times heavier than 1/12 of mass of carbon-12 atom. This is the mass of one ammonia molecule in grams. Even this is the mass of one ammonia molecule in grams. Am I clear with this? If I'm clear with this, then let me define the term molecular mass. I would say molecular mass is a number. Molecular mass is a number which gives an idea about how many times a molecule is heavier than 1 AMU, or you just can write 1U. Okay? Perfectly done. And if this is perfectly done, my dear students, 2 things I'm going to write over here, which will clarify all your doubts from now onwards. Understand what I'm going to say. I'm writing N here. I'm writing N2 here. What is the difference between N and N2? Just tell me that. What is the difference between N and N2? I would say here nitrogen I have taken in atomic form. Here nitrogen I have taken in atomic form. Here nitrogen I have taken in which form? In molecular form. In molecular form, right? On one side, nitrogen in atomic form. On another side, nitrogen in molecular form. Now some terminologies I'm mentioning. The first terminology, I'm writing 14 AMU. Second terminology, only 14. Third terminology, 14 multiplied by 1.66 into 10 raised power minus 24 grams. On this side, N2, the first term, 28U. Second term, only 28. Third term, 28 multiplied by 1.66 into 10 raised power minus 24 grams. Tell me the meaning of all this stuff quickly. Tell me the meaning of all this stuff quickly. See guys, this 14 AMU, since nitrogen in atomic form, I would be calling this as atomic mass of nitrogen. This is what you call as relative atomic mass of nitrogen. This is what I call as the actual mass of N. This is what I call as the actual mass of N. 28U. I would be calling this as, tell me, since nitrogen here is in molecular form, this is what I'll be calling as the molecular mass of nitrogen. Correct? This is what you call as the relative molecular mass of nitrogen. This is what you will be calling as the actual mass of what? Of N or N2. Actual mass of N2. I believe I'm super clear with this. Say yes or no in the chats. Say yes or no in the chats, people. Perfect? Now, if this is perfect, there is one more terminology which I would want to discuss with you. What is that? That is your molar mass. That is your molar mass. Sometimes you call it as gram atomic mass or gram molecular mass. Now, what does this molar mass mean? How do we exactly define it? Try to understand very carefully. I would say molar mass is nothing. It is defined as the mass of 1 mole of the substance. It is defined as the mass of 1 mole of the substance, and at the same time, it is expressed in either grams or you can say grams per mole. Now, before making you understand what this molar mass is, my dear students, you should first of all know what is meant by 1 mole term. For example, sometimes I am writing 1 mole of a substance. 1 mole of a substance. What does it mean? What does it mean? 1 mole of the substance contains how many particles in total? You just need to tell me that. 1 mole of the substance contains how many particles? 1 mole of the substance contains 6.022 into 10 raised power 23 particles of the substance. And this particular number over here is what you call as Avogadro's number. Right? For example, sometimes I write like this. 1 mole of carbon. What does it mean? It means that I've got 6.022 into 10 raised power 23 carbon atoms. Right? Sometimes, for example, I write 1 mole of carbon dioxide. Carbon dioxide is in molecular form, right? Carbon dioxide. It means that I've got NaCO2 molecules. I've got these many number of CO2 molecules. Sometimes if I say I've got 1 mole of O di-negative ion. 1 mole of O di-negative ion. What does it mean? It means that I've got 6.022 into 10 raised power 23 O di-negative ions. Perfect. So in short, I must say 1 mole of substance contains 6.022 into 10 raised power 23 particles. Right? Right, people? Now, we basically have to discuss about what? We have to discuss about the molar mass. Understand what I'll be saying now. Understand what I'll be saying now. My dear students, I'm writing the term here as molar mass of nitrogen, or leave nitrogen aside, we have taken nitrogen once. Let me write molar mass of oxygen. What is meant by this term? Molar mass of oxygen. What do we mean by this? Molar mass of oxygen means mass of 1 mole of oxygen. Molar mass of oxygen means mass of 1 mole of oxygen. Or I can write, we already know, in 1 mole of oxygen, how many oxygen? I'm sorry. In 1 mole of oxygen, how many oxygen atoms will be there? You know, in 1 mole of oxygen, there would be 6.022 into 10 raised power 23 oxygen atoms. Right? So, instead of mass of 1 mole of O, I can write mass of 6.022 into 10 raised power 23 oxygen atoms. Does not make a difference, one and the same thing. Mass of 6.022 into 10 raised power 23 oxygen atoms. Now tell me one thing. How can you calculate the mass of 6.022 into 10 raised power 23 oxygen atoms? How can you do that? It's a very big number. It's a very big number. How can you calculate the mass of 6.022 into 10 raised power 23 oxygen atoms? Let's try to do one thing. Let's first of all calculate the mass of one oxygen atom. Let's first of all calculate the mass of one oxygen atom. And once we get the mass of one oxygen atom, just multiply that with Avogadro's number. We will be getting the mass of 6.022 into 10 raised power 23 oxygen atoms. That's what we wanted. That is what we wanted. Now, my dear students, just think over it. Mass of one oxygen atom. Mass of one oxygen atom means what? Means atomic mass of oxygen. How much that is? That is 16 AMU. Here, you are multiplying with Avogadro's number. I can write it as 16. Instead of this AMU, I can write 1 divided by Na grams. Already there is Na. So Na gets cancelled. The value comes out to be 16 grams. So what is the 16 grams here? What is the 16 grams here? The 16 grams is basically the molar mass of oxygen. Molar mass of oxygen. The 16 grams is basically the mass of 1 mole of oxygen. 1 mole of oxygen. The 16 grams is the mass of 6.022 into 10 raised power 23 oxygen atoms. Understood? Understood, guys? This is the mass of 1 mole of O. This is the mass of 6.022 into 10 raised power 23 oxygen atoms. Now, one more thing. Have I taken oxygen in atomic form? Yes, I have taken oxygen in atomic form. Yes, I have taken oxygen in atomic form. Therefore, instead of molar mass of O, you can write it as the gram atomic mass of O as well. The gram atomic mass of oxygen as well. Sometimes you'll be directly calling it as molar mass of O, or sometimes you can call it as the gram atomic mass of oxygen. One thing, guys, which you have to understand here. Just one thing. Tell me, what was the atomic mass of oxygen? Atomic mass of oxygen was 16 AMU. What is the molar mass of oxygen? 16 grams. 16 AMU atomic mass. 16 grams molar mass. So magnitude-wise, they are same. It is just the units are different. So whenever you are supposed to convert atomic mass into molar mass, do not do anything with the magnitude. Change the units. From AMU, write grams. That's it. Okay? Nitrogen. Atomic mass 14 AMU. Molar mass 14 grams. Right? Sodium. Atomic mass 23 AMU. Molar mass 23 grams. Perfect? Now, let me quickly summarize all this in detail. Let me quickly summarize all this, people. Let me quickly summarize all this. Understand what I'll be saying. And you are going to tell me the answers. You are going to tell me the answers. For example, here I'm writing O. Here I'm writing O2. Tell me the meaning of all this stuff. Oxygen here I have taken in which form? Atomic form. Oxygen here I have taken in which form? Molecular form. Molecular form. Here I am writing 16 AMU. Second thing, 16. Third thing, 16 multiplied by 1.66 into 10 raised power minus 24 grams. Now, instead of 16 AMU, I am writing 16 grams. Same on this side. 32U. 32 multiplied by 1.66 into 10 raised power 24 grams. Instead of 32U, I'm writing 32 grams. You need to tell me the meaning of all these terms. You need to tell me the meaning of all these terms. Sir, have you scheduled a session for 12th also? 12th is already covered. Check, go into the live session. Go into the live category. You will find a session which I took, I think, a week or 10 days back. That is class 12 physical chemistry. Okay. My dear students, this 16 AMU is what? It's your atomic mass. 16, relative atomic mass. This particular term, actual mass. Actual mass of what? Actual mass of O. This is what you call as molar mass of O. Or, since oxygen is in atomic form, You can call this as the gram atomic mass of oxygen as well. Gram atomic mass of oxygen as well. What about the 32U? It is nothing but it is the molecular mass of oxygen. This particular term is relative molecular mass of oxygen. This particular term, actual mass of what? Actual mass of O2. This term is your molar mass of O2, or you can say it is the gram molecular mass of what? Of oxygen. Is it clear? Tell me once in the chats if it is clear. Everybody, people. Everybody. Yes or no in the chats quickly. Are all these things clear? Wonderful. So here I'm writing a note. What is a note? Remember this. I'm writing molar mass of the substance. Molar mass of the substance is nothing but it is the mass of one particle of the substance in grams. Molar mass of the substance is equal to the mass of one particle of the substance in grams multiplied by what? Multiplied by Avogadro's number. I hope this particular statement is also clear. Right? So in short, we can do once like this. Molar mass of the substance. What is it? Mass of 1 mole of substance. Mass of 6.022 into 10 raised power 23 particles of the substance, which is nothing but mass of one particle of the substance. Multiply that with Avogadro's number. That's all. Am I clear with this? Am I clear with this, people? Quick. Everybody in the chats? I believe yes. And if I'm clear with this, what do we do the next? The next is going to be your average atomic mass. Average atomic mass, which I'm representing with MAV. Remember, from this particular concept, questions have been asked, questions will be asked too. Okay? Average atomic mass. So people, what this average atomic mass exactly is all about? First of all, have you heard about the term isotopes? Have you heard about the term isotopes? What are isotopes exactly? Isotopes are basically the atoms. Isotopes are basically the atoms. The atoms of same element. Atoms of same element having same atomic number. Having same atomic number, but different mass numbers. This is something I believe you already know. Now we will try to understand. For example, imagine that I've got the element hydrogen. Everybody knows this, hydrogen. You know, hydrogen has got 3 atoms. Hydrogen has got 3 atoms which have got same atomic number. Hydrogen have got 3 atoms which has got same atomic number but different atomic masses. 1, 2 and 3. Hydrogen, it has got 3 atoms which have got same atomic number but different mass number. What do I call these 3 atoms as? I would be calling them as isotopes of hydrogen. I would be calling them as isotopes of hydrogen. Similarly, let's say I've got chlorine. I've got chlorine. Chlorine has got 2 atoms which have got same atomic number but different atomic masses. So what do I call these atoms as? I would be calling these atoms as the isotopes of chlorine. So what are isotopes in general? Isotopes are the atoms of same element which have got same atomic number but different atomic masses. That's it. Right? Now, my dear students, whenever we have got the element, whenever we have got such an element that has isotopes, such an element that has isotopes, for that element, what do we define? For that element, we define average atomic mass. For that element, we define average atomic mass. Now the point is, how do we calculate this average atomic mass? Now the point is, how do we calculate this average atomic mass? Let's try to get to know how to calculate this average atomic mass. Understand, guys. For example, you have got the element X. Assume that this element has got 3 isotopes. Assume that this element has got 3 isotopes. Same atomic number, different atomic masses. M1, M2, M3. These are the isotopes of X. These are the isotopes of X. Now we know whenever an element has isotopes, what do we calculate for it? Average atomic mass. In order to calculate average atomic mass of this element, what do we need? What do we need? We need percentage abundances or mole percentage of these isotopes. What are percentage abundances? You'll get the idea in some time. Just first of all, remember, whenever you have got the element which has got isotopes, for that particular element, we define average atomic mass. In order to calculate the average atomic mass, what do we need? We need the percentage abundances of these isotopes, right? What are percentage abundances? I'll let you know that in some time. But the percentage abundances which I'm talking about, they are represented by A, B, and C. I'm assuming the abundance of this isotope is A%, this isotope is B%, this isotope is C%. And once we get these percentage abundances, we are directly going to generate a formula. Formula is going to be M1 multiplied by A plus M2 multiplied by B plus M3 multiplied by C divided by what? Divided by A plus B plus C. This is the result with the help of which you can calculate the average atomic mass of an element that has isotopes. That has isotopes, right? Now, try to understand carefully. Try to understand carefully. My dear students, for example, you are taking chlorine. You know chlorine has got 2 isotopes. What all? Cl35, Cl37. These are the isotopes of chlorine. If chlorine has isotopes, we can calculate its average atomic mass. We can calculate its average atomic mass. In order to calculate average atomic mass, what do I need? I need the percentage abundances of its isotopes, right? Let me tell you, experimentally, it's observed that the abundance of this particular isotope is 75% and this is 25%. So what is meant by this? It means that out of all the chlorine in nature, I would say 75% of chlorine would be existing in the form of Cl35. And remaining 25% of the chlorine will be existing in Cl37. For example, imagine in this particular room right now. Imagine in this particular room right now, there are 100 chlorine atoms. Imagine that. There are total 100 chlorine atoms in this room. I would say among those 100 chlorine atoms, some of the chlorine atoms will be of the form Cl35. Some of the chlorine atoms will be of the form Cl37. But from this data, we can conclude 75 chlorine atoms in this room will be of which form? Will be of this form. And 25 chlorine atoms in this room will be of which form? Will be of Cl37 form. Right? Now, my dear students, we got the percentage abundances of the isotopes. So, let me call this as M1. Let me call this as M2. Let me call this as A. Let me call this as B. Do we know the result? Yes, we know the result. What is the result all about? It is nothing but M1A plus M2B divided by A plus B. You know all the things. What is M1? 35. What is A? 75. What is M2? 37. What is B? 25 divided by A plus B comes out to be 100. And my dear students, after solving, this value comes out to be 35.5 AMU. So what is this 35.5 AMU? What is this 35.5 AMU? It is the average atomic mass of chlorine. It is the average atomic mass of chlorine. It is the average atomic mass of chlorine. Right? Perfect. Am I clear, guys? Someone is saying, sir, please go fast. Don't worry. I know. What do I have to do? Okay, just learn what I'm teaching. You don't teach me, what do I do? All right. I hope this is clear to everyone. Now, my dear students, one more thing. If you look carefully, this A plus B is going to be what? 75 plus 25. Comes out to be 100. Comes out to be 100. So remember from now onwards, the sum of percentage abundances. The sum of percentage abundances of all the isotopes. The sum of percentage abundances of all the isotopes of a particular element. Of a particular element is always equal to what? Is always equal to 100. Or I can say simply A plus B plus C value, it's always equal to 100. I hope this is clear to everyone. Yeah? Am I clear? Am I clear, people? Yes or no in the chats quickly. Am I clear? Am I clear? This was one of the questions asked long back in your JEE examination, and I believe you can easily kill this question. I believe you can easily kill this question. Look at it carefully. The question is, you have got boron. Boron has two stable isotopes. Boron has two stable isotopes, B10, B11. B10 and B11. As per the question, the percentage abundance of B10 is given to me as 19. B11 is given to me as 81. Right? So what do? We call this as M1, we call this as A, we call this as M2, and we call this as B. Now what do we calculate? We calculate M average. M average is nothing but M1A plus M2B divided by A plus B, which is always 100. M1 is given, A is given, M2 is given, B is given. Put all the data in this expression. So it's 10 multiplied by 19 plus 11 multiplied by 81 divided by 100. And this value after solving comes out to be 10.81 AMU. So what is this basically? This is your average atomic mass of boron, which I was supposed to calculate. Is this clear, guys? I hope you can solve each and every question based on this particular concept from now on. Is it clear? Say yes quickly. Is it clear? Say yes quickly. Quickly, people. I want everyone to say it. I want everyone to say it. Is this concept clear? Amazing, amazing, amazing. Let's move on. Let's move on. My dear students, there is a term called as calculation of moles. Calculation of moles. How do we calculate moles of any substance? How do we calculate moles of any substance? So first of all, number of moles of a substance. How do we calculate it? There are few results which I would want all of you to remember to calculate moles of any substance. Moles of sodium, moles of NaCl, moles of calcium carbonate, moles of Me, moles of phone, moles of everything. Right? How do we calculate moles of any substance? Number of moles are calculated by the result. What is that? Given mass of the substance in grams, given mass of the substance in grams, divided by the molar mass of the same substance. Given mass of the substance in grams, divided by molar mass of the same substance. This is the first result with the help of which we can calculate number of moles of any substance. Given mass divided by its molar mass. For example, calculate the number of moles. Calculate the number of moles present in 160 grams of NaOH. We are given with 160 grams of NaOH. We are given with 160 grams of NaOH. We have to calculate the number of moles. So first of all, check it out. What am I given with? I'm given with mass of NaOH. I'm given with mass of NaOH in grams, right? I have to calculate moles. So given mass of the substance divided by its molar mass. Given mass of the substance is 160. Molar mass of NaOH would be 23 plus 16 plus 1. That is 40. So divided by 40 grams per mole. The value comes out to be 4. The value comes out to be 4. So it's completely your choice. Whether you want to say that we have got 160 grams of NaOH, or you can say we have got 4 moles of NaOH. The choice is all yours. Whether you want to say we have got 160 grams of NaOH, or you can say we have got 4 moles of NaOH. The choice is all yours. This was formula number 1 to calculate moles of a substance. Number 2. Number of moles is also equal. Number of moles is also equal. Given number of particles, which can be given number of atoms, given number of molecules, given number of ions, right? So in short, given number of particles divided by Avogadro's number. Given number of particles divided by Avogadro's number. This again gives me the number of moles of a substance. For example, have a look. Calculate the number of moles in 24 into 10 raised power 23 atoms of carbon. Atoms of carbon. So what are we given with? We are given with the particles. We are again given with the particles. And if we are given with the particles, we know how to convert moles from particles, right? I'll say number of moles of carbon is equal. Given number of particles divided by Avogadro's number, which is approximately 6 into 10 raised power 23, the value comes out to be 4. Now again, I'm saying it's completely your choice to say that either we have got 24 into 10 raised power 23 atoms of carbon, or we can say we have got 4 moles of carbon. That's it. You can say we have got these many atoms of carbon, or you can say we have got 4 moles of carbon. Choice is all yours. Look at the next one. Calculate the number of moles present in these many molecules of water. Again, we are given with the number of molecules. So again, we are given with the number of particles. Again, we are given with the number of particles. So how do we calculate moles from particles? It is equal. Given number of particles, 48 into 10 raised power 24, divided by what? Divided by Avogadro's number. The value comes out to be 80, right? So whether you want to say we have got these many molecules of water, or you can say we have got 80 moles of water, the choice is all yours. One and the same thing. Now, the next result, with the help of which you can calculate moles of a substance. I'll write number of moles of the gas. This particular formula is only valid for gas. Whatever I'm giving you now, it's only valid for gas. Number of moles of the gas, and gas has to be present at STP. I'm just considering STP, NTP same here in this chapter. Okay. So, number of moles of the gas at STP is equal to what? It is equal to given volume of the gas in liters divided by 22.4 liters. Given volume of the gas in liters divided by what? Divided by 22.4 liters. This is one more result with the help of which we can calculate moles of a gas. For example, look at this particular question. Calculate the number of moles present in 67.2 liters of carbon dioxide. 67.2 liters of carbon dioxide at STP. What are we given with? We are given with volume of the gas. And we know how to convert volume into moles. We know how to convert volume into moles. It is given volume of the gas in liters divided by 22.4 liters. Value comes out to be 3. Now, whether you want to say we have got 67.2 liters of carbon dioxide, or you can say we have got 3 moles of carbon dioxide, the choice is all yours. It's one and the same thing. Am I clear with this? Say it in the chats, quick. Say it in the chats, people. Everybody. Everybody. I want everyone to say it. Are you getting all the things properly? Is it all clear? I want the chats to run. Don't make the chats to crawl. I want the chats to run. How many hours it will take to complete mole concept? It will take 4.5 hours. Perfect. Perfect. Now, my dear students, one simple diagram I'm giving you, which will ease out a lot of things, right? Which will be helpful for us. Which will be helpful for us. Okay? Understand what I'll be doing. First of all, I'm writing a term here. Number of moles. I'm writing the term number of moles. How many ways did we see to calculate number of moles? We saw 3 ways to calculate number of moles. We saw 3 ways. First way, sometimes you will be given with the mass of the substance in grams. Okay. Sometimes you'll be given with the number of particles of the substance. Right? And sometimes you'll be given with volume of the gas at STP. These can be 3 things given to us to calculate the moles. These can be 3 things given to us to calculate the moles. Now, my dear students, you already know. If mass of the substance is given and you are supposed to calculate moles, then what do? Given mass of substance divided by molar mass of the substance. That gives us moles, right? Or if I do the reverse, if moles are given, mass is to be calculated. If moles are given, mass is to be calculated. Then what do? Moles of the substance multiplied by molar mass of the substance. That gives me the mass. Simple. Given mass divided by molar mass. Moles multiplied by molar mass. That gives me mass. Number 1. Number 2. Given number of particles divided by Avogadro's number. That gives me moles. Or reverse. Moles multiplied by Avogadro's number. That gives me particles. Volume of the gas divided by 22.4 liters. Gives me what? Gives me moles. Or moles multiplied by 22.4 liters. Moles multiplied by 22.4 liters gives me the volume of the gas. These are the 3 simple things which I would want you guys to remember. Okay? Now, where do we use this diagram? That is the point. So have a look. Where do I use it? For example, look at this question. Calculate the mass of 67.2 liters. Calculate the mass of 67.2 liters of carbon dioxide at STP. We are supposed to calculate mass. What are we given with? We are given with volume. We are supposed to calculate mass and we are given with volume. Okay. So I will start from volume and I'll follow all the arrows which will take me from volume to mass. I'll start from volume and I'll be following all the arrows which will take me from volume to mass. So what is going to be my first arrow? This is the first arrow which I'll be following. This is the second arrow I'll be following. So how many steps? 2 steps. First step is going to be conversion of volume into moles. Second step, moles into mass. So 2 steps I have. So if I write the answer of the first question, what is it going to be? What is my first step? First step is conversion of volume into moles. Number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by 22.4 liters. The value comes out to be 3. So I'm done with this particular conversion. Now moles into mass. How? Moles multiplied by molar mass, that gives me mass. Right? So I'll say mass of carbon dioxide in grams will be equal to moles of carbon dioxide multiplied by what? multiplied by molar mass of carbon dioxide. So this is 3. Molar mass of carbon dioxide is 44. The value comes out to be 132 grams. Simple. Right? So I can clearly say the mass of 67.2 liters of carbon dioxide is how much? That is 132 grams. That's it. Nothing else. Nothing else, guys. All right. Second one. Calculate the number of molecules present in 440 grams of carbon dioxide. You are given with mass. You are supposed to calculate molecules. Given with mass. We are given with mass and we have to calculate molecules. Molecules means particles. Given with mass, we are supposed to calculate particles. So I'll be starting with mass and I'll have to reach to particles. I'll be following all the arrows that take me from mass till particles. So what all arrows I'll be following? Simple. Given mass, divided by molar mass, gives me moles. Moles multiplied by Avogadro's number, that gives me particles. So how many steps? 2 steps. First step is going to be the conversion of mass into moles. Second step, moles into molecules. So 2-step question this is. So first thing I'll be doing, number of moles of carbon dioxide is equal to given mass of carbon dioxide in grams divided by molar mass of carbon dioxide. The value comes out to be 10. So these are the moles of carbon dioxide which we have, right? Now people, from moles to molecules to particles. So I'll say molecules of carbon dioxide will be equal to moles of carbon dioxide multiplied by Avogadro's number. Moles are 10 multiplied by Avogadro's number. So these many molecules we have. Am I clear with this? Am I clear with this, people? Quickly in the chats. Look at the next question. And I believe you can easily solve this one. The mass of one atom of X is this much. So X is an element. And the mass of one atom of X is given. What are we supposed to calculate? Calculate the number of moles present in 96 kg. 96 kg means 96000 grams. So we are given with a mass of X. What are we supposed to calculate? We are supposed to calculate moles. What are we given? We are given with mass of an element. We are supposed to calculate its moles. Done. Number of moles of X is equal to mass of X in grams divided by the molar mass of X. Divided by the molar mass of X. Right? Mass of X is nothing but, that is 96000 grams divided by. Molar mass of X is not given to me. Molar mass of X is not given to me. But we can calculate molar mass of X. How do we calculate molar mass? Molar mass of a substance is equal to mass of one particle in grams multiplied by Avogadro's number. I've discussed that. What is the mass of one particle of X? That is 4 into 10 raised power minus 23 grams. Multiplied by what? Approximately Avogadro's number 6 into 10 raised power 23. So this term cancel. 6 4s are 24. So this is the molar mass of X. So it's going to be 96000 divided by 24. The value comes out to be, I think, 4000. Right? So now it's completely your choice to say that we have got 96000 grams of X, or you can say we have got 4000 moles of X. Am I clear with this? Am I clear with this? This is a question which is asked long back in your JEE examination. A simple and basic question. How many moles of electrons? How many moles of electrons weighs 1 kg? 1 kg means 1000 grams. Understand the language of the question. How many moles of electrons weighs 1 kg? So we are given with mass of electron. We are supposed to calculate moles of electron. Right? So I would simply say number of moles of electron is nothing but mass of electron in grams divided by molar mass of electron. What is the mass of electron in grams? That is 1000 grams. What is the molar mass of electron? I do not know the molar mass of electron, but we can calculate it. Molar mass of electron will be mass of one electron in grams multiplied by Avogadro's number. Now this would be the molar mass of electron. It is just a matter of calculation and you are done. Yes. Am I clear with this, guys? Are you understanding all this stuff? Perfect. Perfectly done. Now comes one more basic topic, which is again asked in the examination. What is that? You are asked some questions in which you are supposed to do the calculation of atoms, the calculation of electrons, calculation of protons, calculation of neutrons, calculation of valence electrons. All this stuff is asked. All this stuff is asked. Okay? Now, people, whenever we are supposed to calculate atoms, electrons, protons, neutrons, ions, valence electrons, anything out of this, again, I would want you guys to remember something. What is that something? See, guys, I'm writing a term here as given quantity. I'm writing the term here as given quantity. Whatever will be given to you in the question, whatever is given in the question, whether it is the mass of the substance, whether it is volume of the substance, particles of the substance, whatever is given in this question, all that is given quantity. The first step always is to convert given quantity into moles. The first step always is going to be the conversion of given quantity into moles. Once we get the moles of substance, moles are to be multiplied with Avogadro's number. Moles are to be multiplied with Avogadro's number. Okay? Moles are to be multiplied with Avogadro's number. You will be getting the molecules if the given substance is in molecular form. You'll understand this in some time. Okay? Given quantity into moles. Moles multiplied by Avogadro's number gives me the molecules of the substance if the substance is in molecular form. Once we get molecules, from there, you can easily calculate atoms, you can easily calculate electrons, you can easily calculate protons, you can easily calculate neutrons, you can easily calculate valence electrons, anything can be asked. Okay? Now, one more thing. If the given substance is in atomic form, then moles multiplied by Avogadro's number, it directly gives me the atoms. If given substance is in molecular form, then moles multiplied by Avogadro's number gives me molecules. If given substance is in atomic form, then moles multiplied by Avogadro's number gives me atoms. And remember, if the given substance is in ionic form, then moles multiplied by Avogadro's number gives me ions directly. These are the three things which I would want all of you to remember from now onwards. Okay? What is the first step? Given quantity into moles. Then moles multiplied by Avogadro's number gives you molecules if substance is in molecular form. Gives you atoms if atomic form. Gives you ions if in ionic form. Let's do a question so that you can understand this. The question is, calculate the total number of atoms. Calculate the total number of atoms in 448 liters of carbon dioxide gas. What am I given with? Check the given quantity. We are given with volume. We are supposed to calculate atoms. Given with volume, supposed to calculate atoms. Given with volume, my given quantity is volume. What am I supposed to calculate? Atoms. I'll be using this diagram. Step by step. What is the first thing? Convert the given quantity into moles. So, number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by 22.4 liters. The value comes out to be 20. Right? So, whether you want to say that we have got 448 liters of carbon dioxide, or you can say we have got 20 moles of carbon dioxide. One and the same thing. We have calculated moles. The second step is moles multiplied by Avogadro's number. Gives you what? It can give you atoms, it can give you molecules, it can give you ions. Depending on the substance. This substance, is it in atomic form or molecular form? It is in molecular form. So what do I get from here? I'll be getting molecules. So molecules of carbon dioxide is equal to moles multiplied by Avogadro's number. So it's 20 Na. So it's 20 Na. So people, these are the molecules of carbon dioxide we have. It's completely your choice whether you want to say we have got 448 liters of carbon dioxide, or you can say we have got 20 moles of carbon dioxide, or you can say we have got these many molecules of carbon dioxide. Completely your choice. So we have done the calculation till molecules. We have done the calculation till hair. Now, what after this? Atoms. What after this? Atoms. Now you tell me. I'm not going to do anything. You are going to tell me one thing. If I ask you, one molecule of carbon dioxide contains how many atoms? You tell me. One molecule of carbon dioxide contains how many atoms? 2 plus 1, 3 atoms, right? Simple. One molecule of carbon dioxide contains 3 atoms. People, it's evident. If one molecule of carbon dioxide contains 3 atoms, therefore, 2 molecules of carbon dioxide will contain, multiplied by 2. 3 molecules of carbon dioxide multiplied by 3. 4 molecules of carbon dioxide multiplied by 4. How many molecules of carbon dioxide we have? 20 Na. So 20 Na molecules of carbon dioxide will contain 3 multiplied by 20 Na. The value comes out to be 60 Na atoms. 60 Na atoms, right? So these many atoms will be there in total in 448 liters of carbon dioxide. Am I clear with this? Am I clear with this, people? For example, this is one more question, and it's asked question. It has been asked once. The question is, calculate the valence electrons. Calculate the valence electrons. In what? In 4.2 grams of N tri-negative. In 4.2 grams of N tri-negative. What is the first step? Convert the given quantity into moles. So number of moles of N tri-negative will be equal to given mass of N tri-negative divided by molar mass. What is the molar mass of nitrogen? You know, that's 14. The value comes out to be 0.3. So these many moles of N tri-negative we have. What is the second step? Second step is moles multiplied by Avogadro's number. That can give you molecules, that can give you atoms, that can give you ions. For that, check the given substance. The given substance is in ionic form. The given substance is in ionic form. So here, I'm doing the calculation of ions. Number of ions of N tri-negative. Number of ions of N tri-negative will be equal to 0.3 Na. So these many ions of N tri-negative we have. Since you got the ions, what is the next thing? What is the next thing? Ions we have calculated. Now we have to calculate the valence electrons. How exactly? How exactly? Understand, guys. If I talk about nitrogen, whose atomic number is 7, right? And here it has got tri-negative charge. If I ask you how many electrons will be there in N tri-negative, you will say 7 plus 3, 10 electrons. There are 10 electrons in one N tri-negative. These 10 electrons are distributed. 2 in the first shell, 8 in the second shell. They are distributed. 2 in the first shell, 8 in the second shell. And these 8 electrons which are in the second shell, I'll be calling them as the valence electrons. Simple. So can I simply say one N tri-negative ion? Can I simply say one N tri-negative ion contains how many valence electrons? 8 valence electrons. If one N tri-negative ion contains 8 valence electrons, 2 N tri-negative ions will contain multiplied by 2, 3 N tri-negative multiplied by 3, 4 multiplied by 4. How many N tri-negative ions we have? 0.3 Na. So I would say 0.3 Na N tri-negative ions will contain 8 multiplied by 0.3 Na N tri-negative ions, which is 2.4 Na N tri-negative ions. Am I clear with this? Am I clear with this, people? Quickly, let me know in the chats. All this stuff you can do easily from now onwards. Now comes one more concept which is frequently asked. Let's have a look on that. The next concept is calculation of moles of atoms and molecules. Calculation of moles of atoms and molecules. This is pretty much simple, guys. Pretty much simple. Understand. For example, I'm writing a term 1 mole glucose. 1 mole glucose, okay? 1 mole glucose. Can I say in 1 mole of glucose, you will find 6 moles of carbon. You will find 12 moles of H. You will find 6 moles of O. Yes, we can do that. We can do that, right? I'll say 1 mole of glucose. It contains 6 moles carbon, 12 moles H, 6 moles of O. Tell me one thing. Here hydrogen I've used in atomic form. Here hydrogen I've used in atomic form. Hydrogen is used in atomic form. Let me first of all tell you, moles are sometimes called as gram atoms, or sometimes you can call them as gram molecules. These are some new terminologies which are used instead of moles. You can call moles as gram atoms, gram molecules, gram ions, etc. See, hydrogen here is in atomic form. So instead of term mole, you can also write, 12 gram atoms of hydrogen, right? You can write 12 gram atoms of hydrogen. Now, here oxygen is also in atomic form. So instead of term moles, you can write 6 gram atoms of oxygen. 6 gram atoms of oxygen. This is point number 1. This is your point number 1. This is your point number 1. Point number 2. Point number 2. The same statement I'm writing. I'm writing 1 mole glucose. 1 mole glucose. First of all, you know, it contains 6 moles of carbon. Yes, it contains 6 moles of carbon. And it contains 12 moles of H. 12 moles of H. And here hydrogen I've taken in atomic form. If I want to take hydrogen in molecular form, can I say instead of 12 moles of H, can't we write 6 moles of H2? Because 6 moles of H2 means 12 moles of H. Simple. 6 moles of H2 means 12 moles of H. Similarly, instead of 6 moles of O, can't I write 3 moles of O2? Yes, I can do that. Right? I can do that too. Now guys, if you think logically, here hydrogen I have taken in molecular form. If hydrogen is in molecular form, then instead of moles, I can write 6 gram molecules of hydrogen. 6 gram molecules of hydrogen, right? Similarly, oxygen here is in molecular form. I can write 3 gram molecules of oxygen. I can write 3 gram molecules of oxygen. I believe this particular point is clear. I believe this particular point is clear to everyone. Is it? Say yes or no in the chats quick. Say yes or no in the chats quick. If yes, let's try to solve this particular question. Let's see what the question is. Calculate the moles of O. Calculate the moles of O present in 196 grams of H2SO4. This is my given quantity. Always convert the given quantity into moles. Now, number of moles of H2SO4 will be equal to given mass of H2SO4 in grams divided by molar mass of H2SO4. The value comes out to be 2. So technically you can say that we have got 2 moles of H2SO4. Technically we can say that we have got 2 moles of H2SO4. Now people just tell me one thing. The general data. 1 mole H2SO4 contains how many moles of O? It contains 4 moles of O, right? 1 mole H2SO4 contains what? It contains 4 moles of O. If 1 mole H2SO4 contains 4 moles of O, how many moles of H2SO4 we have? 2. So tell me, 2 moles of H2SO4 will be containing 4 2s are 8 moles of O. Isn't this what we were supposed to calculate? I got to know 8 moles of O are present in 2 moles of H2SO4. Or I can say 8 moles of O are present in 196 grams of H2SO4. Simple and basic. Simple and basic. Let's move on to the next one. Move on to the next one. Look at this question. This is also one asked question in JEE Mains. Look at it. Calculate the mass of H3PO4. Calculate the mass of H3PO4 that contains 0.25 moles of O. In what mass of H3PO4? In what mass of H3PO4 there will be 0.25 moles of O? You can do that. You can do it, people. See, it's again very much simple. See, if you talk about H3PO4, understand, can I say 4 moles of O? 4 moles of O are present in 1 mole H3PO4. Is the statement correct? Is the statement correct? Thank you, Lofty Love. Is the statement correct? It's a general statement, guys. A general statement. 4 moles of O. 4 moles of O are present in 1 mole H3PO4. Pretty much clear? Use the unitary method. If I use the unitary method says that if 4 moles of O are present in 1 mole H3PO4, therefore 1 mole O would be present in 1 by 4 moles of H3PO4. Therefore, 1 mole O would be present in 1 by 4 mole H3PO4. Simple. How many moles of O we have? 0.25. I would say 0.25 moles of O would be present in 1 by 4 moles of H3PO4. Just a second. 0.25 moles of O would be present in 1 by 4 multiplied by 0.25 moles of H3PO4. Is this statement correct? Yes. And when you solve this, this value comes out to be 1 by 16 moles of H3PO4. 1 by 16 moles of H3PO4. Right? So people, I got to know 0.25 moles of O, 0.25 moles of O are present in these many moles of H3PO4. Are present in these many moles of H3PO4. Right? So what did I get? I got the moles of H3PO4. But what am I supposed to calculate? I'm supposed to calculate mass. How do you convert moles into mass? I can say mass of H3PO4 would be equal to moles of H3PO4 multiplied by molar mass of H3PO4. When you solve this, the value comes out to be 6.125 grams. So these many grams of H3PO4, these many grams of H3PO4 will contain 0.25 moles of O. Is this particular question very much clear to everyone? Tell me in the chats, people. Tell me in the chats. Tell me in the chats quickly. Yes. Everyone in the chats, quick. Everyone in the chats, quick. Want the chats to be running quickly. Perfect, guys. Now let's move on to one more amazing topic. What is that? That is stoichiometry. It forms the basis of everything. It forms the basis of everything, okay? Right? So let's get going. Stoichiometry. See, guys, let me take a general example, a general chemical reaction, any chemical reaction, whatever you would want to take, any chemical reaction. For example, I'm taking the reaction as N2 gas plus H2 gas. It gives NH3 gas. Is it a balanced chemical equation? No, it's not the balanced chemical equation. Let's do one thing. Let's try to balance this reaction. When we balance this reaction, this becomes 3 times, this becomes 2 times, this becomes 1. Now, after balancing this reaction, this 1, 3, and 2, 1, 3, and 2, I'll be calling them as, the stoichiometric coefficients. I'll be calling them as the stoichiometric coefficients. And let me tell you, these stoichiometric coefficients, they are treated as moles. These stoichiometric coefficients, they are treated as moles. Now, from the stoichiometric coefficients of reactants and products, what can I understand? I can say, from the stoichiometry of the reaction, I can say 1 mole N2, 1 mole N2 completely reacts with 3 moles of H2. 1 mole N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. This particular information is given by the stoichiometric coefficients of reactants. Okay? This particular information is given by the stoichiometric coefficients of reactants products. You got to know 1 mole N2 completely reacts with 3 moles of H2 and produces what? It produces 2 moles of NH3. Okay? This is one information which I am writing in terms of moles. This is one information which I'm writing in terms of moles. The second information. First of all, what is the molar mass of N2? What is the molar mass of N2? 28 grams. That means mass of 1 mole of N2 is 28 grams. Molar mass of N2 is 28 grams. What does that mean? That means the mass of 1 mole of N2 is 28 grams. We have got just 1 mole of N2 here. So instead of 1 mole of N2, I can just write 28 grams of N2. Okay. What is the molar mass of H2? Molar mass of H2 is 2 grams. Molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. But do I have 1 mole of H2 or 3 moles of H2? I've got 3 moles of H2. If mass of 1 mole of H2 is 2 grams, therefore mass of 3 moles of H2 is 6 grams. So I'm writing 6 grams of H2. Okay. What is the molar mass of NH3? It would be 14 plus 3, 17 grams. It would be 17 grams. Therefore, I can say mass of 1 mole of NH3 is 17 grams. So mass of 2 moles of NH3 is 17 into 2, 34 grams. Okay. So from the stoichiometric coefficients of reactants and products, I got to know 28 grams of N2 completely reacts with 6 grams of H2 and produces what? It produces 34 grams of NH3. And this kind of information, right, which is directly in terms of mass, again I got from the stoichiometric coefficients. So this information is in terms of mass, which I again got from the stoichiometric coefficients of reactants products. The third information is in terms of volume. Let me tell you, I can treat these stoichiometric coefficients directly as volume as well. I can say 1 volume of N2 completely reacts with 3 volume of H2 and produces 2 volume of NH3. 1 volume of N2 completely reacts with 3 volume of H2 and produces 2 volume of NH3. Now what does that mean? That simply means you can take volume in liters. When you take volume in liters, you can say 1 liter N2 completely reacts with 3 liters of H2 and produces 2 liters of NH3. Or you can take this volume in terms of ml as well. You can say 1 ml N2 completely reacts with 3 ml H2 and produces 2 ml NH3. The choice is all yours. So technically all this information about the reaction is given by what? Is given by the stoichiometric coefficients of reactants and products. It is given by the stoichiometric coefficients of reactants and products. I hope I'm clear with this. And if we are clear with this, then let's try solving some questions so that you can understand and analyze the things. One of the very common question, basic question I'm starting with. The question is, calculate the mass of O2, produced on heating 12.25 grams of KClO3. So as per the question, as per the question, we have got 12.25 grams of KClO3 with us. As per the question, we have got 12.25 grams of KClO3 with us. Now we are heating this KClO3. When we heat up this KClO3, it gets converted to KCl, and with that, you get O2 gas as well. This is something which we already know, right? When KClO3 is heated, we get KCl and O2. Now, as per the question, when 12.25 grams of KClO3 is heated, what mass of O2 gas is produced? What mass of O2 gas is observed? What mass of O2 gas is liberated? See guys, there are few things which you need to know while solving the questions. Number one, the first step always is going to be to convert the given quantity into moles. Convert the given quantity into moles. What is my given quantity? I am given with mass of KClO3. I am going to convert this given quantity into moles. So how many moles of KClO3 do we have? Given mass of KClO3 in grams divided by molar mass of KClO3. So we have got basically 0.1 moles of KClO3. We have got 0.1 moles of KClO3. We are starting with 0.1 moles of KClO3, right? I've converted the given quantity into moles. Now second, whether you want to say that we have got 12.25 grams of KClO3, or you can say we have got 0.1 moles of KClO3. And we are going to heat up 0.1 moles of KClO3. Now, first of all, look if the reaction is balanced or not. Balance the reaction. Convert the given quantity into moles. After that, balance the reaction. This is 2 times, this is 2 times, this is 3 times. The reaction is balanced. After balancing the reaction, look at these two things. Look at their stoichiometry coefficients. I can say stoichiometry is telling us that when 2 mole KClO3 is heated, 3 moles of O2 are produced. When 2 moles of KClO3 are heated, 3 moles of O2 are produced. Okay? When 2 mole KClO3 are heated, 3 moles of O2 are produced. Now use the unitary method. If 2 moles of KClO3 gives 3 moles of O2, therefore 1 mole KClO3 gives us 3 by 2 moles of O2. Therefore 1 mole KClO3 gives us 3 by 2 moles of O2. But as per the question, do we have to heat up 1 mole of KClO3? No, we have to heat up 0.1 moles of KClO3. So I would say 0.1 mole KClO3 upon heating gives 3 by 2 multiplied by 0.1, which comes out to be 0.15 moles of O2. So these are basically the moles of O2 which are produced. These are the moles of O2 which are produced when 0.1 mole KClO3 are heated, when 12.25 grams of KClO3 are heated. But as per the question, am I supposed to calculate the moles of O2 produced? No, I'm supposed to calculate mass of O2 produced. Mass of O2 produced will be moles of O2 produced multiplied by molar mass of O2. The value comes out to be 4.8 grams. So I would say 4.8 grams of O2 are produced at the end of the reaction. Am I clear with this? Am I clear with this, guys? Am I clear with this? Second thing, calculate the volume of carbon dioxide produced at STP by complete combustion of octane. First of all, if you have got a combustion reaction like this, CXHY plus O2, it gives carbon dioxide and water. And yes, students, there is a general way of balancing the combustion reaction. Remember that? There's a general way of balancing the combustion reaction. If this is X here, the stoichiometric coefficient here is X. If it is Y here, the stoichiometric coefficient here is Y. The stoichiometric coefficient of oxygen would be X plus Y divided by 4. Okay? This is the general way of balancing the reaction. Balancing the combustion reaction. Or for example, if you have got something like this, CXHYOZ plus O2, again it gives carbon dioxide and water. Again, it gives carbon dioxide and water. Right? How do we balance it? This is X. The coefficient here is X. This is Y. The coefficient here is, sorry, this Y by 2 here. Okay? This Y by 2. The coefficient here is Y by 2. The coefficient here is Y by 2. And the coefficient here is X plus Y by 4 minus Z by 2. This is how you balance these reactions. This is how you balance these reactions. I hope I'm clear with this. Okay. Now, guys, let's go into the question. Let's go into the question directly. What is the question saying? The question is saying that calculate the volume of carbon dioxide produced at STP by complete combustion of 570 grams of octane. So we have got octane. We are doing its combustion. And when we do its combustion, what does it give us? Carbon dioxide and water. Okay. What is my first point all the time? To balance the reaction. If this is 8, make this 8. This is 18. 18 by 2 is 9. And this would be x plus y by 4, which comes out to be 25 by 2. Okay. Second step, convert the given quantity into moles. Given quantity is mass. We are given with mass of octane. I want to convert this into moles. So moles of octane would be mass of octane in grams divided by molar mass of octane. The value comes out to be 5. So technically, we have to do the combustion of 5 moles of octane. Now the stoichiometry is telling us that 1 mole octane, when undergoes combustion, it produces 8 moles of carbon dioxide. When 1 mole octane undergoes combustion, it produces 8 mole carbon dioxide. Therefore, when 5 moles of octane will undergo combustion, they'll produce 8 multiplied by 5. They'll produce 40 moles of carbon dioxide. So 40 moles of carbon dioxide are produced here. If you got the moles of carbon dioxide, I need to convert this moles into volume. So volume of carbon dioxide produced would be equal to moles of carbon dioxide produced multiplied by 22.4. The value comes out to be 896 liters. So I would say 896 liters. 896 liters of carbon dioxide would be produced. Okay. I'll give you the break at 2 p.m. exact. Okay. Don't worry. Break will be at 2 p.m. Don't ask me for the breaks continuously. Break will be at 2 p.m. for you as well as me. Okay. I know you are hungry. I'm hungry too. Still, let's wait for some time and let's have the lunch at 2. Got it? Perfect. Let's move on. Let's say you have got this question. on stoichiometry. My dear students, as per this particular question is concerned, we are again given with a balanced chemical equation. This is your balanced chemical equation. This is your balanced chemical equation. The question says that how many grams of NO2 are required to produce 25.2 grams of NH3. We are supposed to produce 25.2 grams of NH3. We are supposed to produce 25.2 grams of HNO3. Right? Well, in order to produce 25.2 grams of HNO3, how many grams of NO2 are required? How do we solve this? First step, convert the given quantity into moles. So number of moles of HNO3 would be equal to given mass of HNO3 in grams divided by molar mass of HNO3. How much this value will be? Can you solve it? Can you check it? I think it will be 0.4, I think. Right? So these many moles of HNO3 we are supposed to produce. Now, in order to produce these many moles of HNO3, what mass of NO2 would be required? Understand. Just use the stoichiometry. See, the coefficient here is 2, the coefficient here is 3. Stoichiometry is telling me that 2 moles of HNO3 are produced. Stoichiometry is telling me that 2 moles of HNO3 are produced from 3 moles of NO2. Right? 2 moles of HNO3 are produced from 3 moles of NO2. Therefore 1 mole HNO3 would be produced from 3 by 2 moles of NO2. Right? Therefore, 0.4 moles of HNO3 0.4 moles of HNO3 would be produced from 0.6 moles of NO2. Right? So these are the moles of NO2 which are required. These are the moles of NO2. These are the moles of NO2 which are required to produce 0.4 moles of HNO3. But am I supposed to calculate the moles of NO2 required or mass of NO2 required? I'm supposed to calculate the mass of NO2 required. So mass of NO2 which is required, that would be moles of NO2 required multiplied by its molar mass. Molar mass would be 32 plus 14 is 46, right? So the value comes out to be 27.6 grams. So I would say 27.6 grams of NO2 would be required to produce 25.2 grams of HNO3. Am I clear with this? Am I clear with this, people? Am I clear with this? Am I clear with this? Now, from the stoichiometry, you can involve the stoichiometry in sequential reactions as well. You can involve the stoichiometry in sequential reactions as well. How exactly stoichiometry is involved in sequential reactions? See, guys, for example, you have got the reaction like this. A plus B, it gives C. Okay. Now, this C over here, it reacts with D and forms E. This E over here, it reacts with some F and forms G. Let's say this is the sequence of the reaction which is happening. Sequence of the reaction which is happening. Now see, understand one thing. My dear students, this C is the product of the first reaction. C is the product of the first reaction. Okay. The same C is the reactant of the second reaction. Okay. This E is the product of the second reaction. The same E is the reactant of the third reaction. Correct? And my dear students, you should know, during the reaction, a reactant is consumed. During the reaction, a reactant is consumed and product is formed. During the reaction, reactant is consumed and the product is formed. Okay? Now try to understand. See, in the first reaction, the C is being formed. Remember, whatever C is formed in the first reaction, all that C is utilized in the second reaction. For example, in the first reaction, let's say 5 moles of C are formed. If 5 moles of C are formed here, all those 5 moles of C would be consumed here. All those 5 moles of C would be consumed here. And eventually E gets formed. Whatever E is formed here, all that E would be getting consumed here. And finally, the production of G will be happening. Finally, the production of G will be happening. This is the simple concept which we have to use. Whatever product is formed here, same product is consumed here. Whatever product is formed here, same product is consumed here. That's it. That's it, and we are done. That's it, and we are done. Have a look how. If you look at this particular reaction, select the common components. KClO, KClO. This is KClO3, KClO3. And finally, what is formed? KClO4 is formed. And we are starting with Cl2. Calculate the mass of KClO4. Calculate the mass of KClO4 formed on starting with 568 grams of Cl2. We are starting with 568 grams of Cl2. What is my first step? Convert the given quantity into moles. So number of moles of Cl2 is equal to given mass of Cl2 divided by molar mass of Cl2. It comes out to be 8. So we are starting with 8 moles of Cl2 in the beginning. We are starting with 8 moles of Cl2 in the beginning. 8 moles of Cl2 we are starting. Now, look at the stoichiometry. 1 mole Cl2 gives 1 mole KClO. If 1 mole gives 1 mole, therefore 8 moles of Cl2 would give 8 moles of KClO. So in the first reaction, 8 moles of KClO are formed. Right? In the first reaction, 8 moles of KClO are formed. Now, whatever KClO is formed here, all that KClO is utilized here. Okay? Now again use the stoichiometry. 3 and 1. I'll say 3 moles of KClO gives 1 mole KClO3. 3 moles KClO gives 1 mole KClO3. 1 mole KClO gives 1 by 3 moles of KClO3. So 8 moles of KClO gives 8 by 3 moles of KClO3. So 8 by 3 moles of KClO3 are being formed in the second reaction. Right? Perfect. So 8 by 3 moles of KClO3 are formed in the second reaction. And whatever KClO3 is formed here, all that KClO3 is utilized here. How? See, this is 4, this is 3. I'll say 4 mole KClO3 gives 3 mole KClO4. Therefore, 1 mole KClO3 gives 3 by 4 moles of KClO4. Therefore, 8 by 3 moles of KClO3 gives 8 into 8 by 3 moles of KClO4. This value comes out to be 2. So you got to know finally 2 moles of KClO4 are formed. Finally, you got to know 2 moles of KClO4 are formed. But am I supposed to calculate moles of KClO4 or mass? I'm supposed to calculate mass of KClO4, right? So mass of KClO4 formed would be equal to moles of KClO4 multiplied by what? Multiplied by molar mass of KClO, right? And you are done. Let's try to solve one more question so that it will be like easy for you. One more question I'm giving you. As far as this question is concerned, let me take the values easy here. Let's say we have got 224 liters of NH3, for example. My dear students, we are starting with 224 liters of NH3 and we have to check what mass of HNO3 is formed at the end. We are starting with NH3, we have to reach at HNO3. What is the first thing? What is the first thing? Convert the given quantity into moles. What is my given quantity? Volume. So I need to convert it into moles. So number of moles of NH3 is equal to given volume of NH3 divided by 22.4. The value comes out to be 10. We are starting with 10 moles of NH3. We are starting with 10 moles of NH3. Now people, understand. Look at the common components. Common components are your, see, this is NO and here you have got NO. NO2, finally HNO3 is formed. We are starting with 10 moles of NH3. Now understand. Stoichiometry tells us that 4 mole NH3 gives us 4 mole NO. 1 mole NH3 gives us 1 mole NO. 10 mole NH3 gives us 10 mole NO. So in the first reaction, 10 moles of NO are formed. In the first reaction, 10 moles of NO are formed. And whatever NO is formed here, it would be utilized here. See, 2 moles of NO gives 2 moles of NO2. 1 mole NO gives 1 mole NO2. So 10 moles of NO gives us 10 moles of NO2. So 10 moles of NO2 are formed here. Look at the next reaction. 3 moles of NO2 gives 2 moles of HNO3. 1 mole NO2 gives 2 by 3 moles of HNO3. Therefore, 10 moles of NO2 gives us these many moles of HNO3. So how many moles of HNO3 are formed at the end? 20 by 3 means 6.66. So these many moles of HNO3 are formed. These many moles of HNO3 are formed. If you got the moles of HNO3 formed, then we have to calculate mass of HNO3. Mass of HNO3 would be moles of HNO3 multiplied by molar mass of HNO3, which is 63. Solve it, get the answer. That's it. Am I clear with this? Am I clear with this, guys? Quickly, let me know in the chats. Quickly, let me know in the chats. Yes? Is it clear? Is it clear? Is it clear? Everybody? Perfect. Now comes one more term, that is vapor density of a gas. That is vapor density of a gas. When will this chapter end? This chapter will still take 2 more hours. It is the biggest of all the chapters. Okay, it will still take 2 more hours. Concept of vapor density. Okay. See guys, imagine I've got 2 containers. Imagine I've got 2 containers. In this particular container, I've got some gas, some random gas. I've got some random gas. In the second container, I'm particularly taking which gas? Hydrogen gas. Okay. This random gas and hydrogen gas, their pressure temperature is same. They are kept at same pressure temperature. Whatever is the pressure of this gas, same is the pressure of hydrogen. Whatever is the temperature of this gas, same is the temperature of hydrogen. At same pressure temperature, this is the density of the gas and this is the density of hydrogen gas. At same pressure and temperature, let the density of gas be something and let the density of hydrogen gas be something. Now we have got a term that is vapor density. Vapor density of the gas. Vapor density of the gas is defined as density of the gas divided by density of hydrogen gas at when both the gases are kept at same pressure and temperature. This is the definition of what? This is the definition of vapor density. Vapor density of a gas is nothing but it is defined as the density of the gas divided by the density of hydrogen gas, provided the gas and hydrogen they are kept at same pressure and temperature. Provided that they are kept at same pressure and temperature. Okay, I hope this is clear. Now, my dear students, understand one thing. There is a result which I am giving you. Okay, I am not deriving the result. Just remember it directly. Remember, molar mass of the gas is always equal to 2 times vapor density of the gas. Molar mass of the gas is always equal to 2 times vapor density of the gas. For example, if you have got a gas, its vapor density is 5. You have got a gas, its vapor density is, for example, 5. If vapor density is 5, that means its molar mass would be 5 to the 10. Okay, 5 to the 10. One more thing. Imagine that if you have got a gaseous mixture. If you have got a gaseous mixture. For the gaseous mixture, how do we write this particular statement? We write molar mass of the gaseous mixture is always equal to 2 times vapor density of the gaseous mixture. Molar mass of the gaseous mixture is always equal to 2 times vapor density of the gaseous mixture. Remember this particular statement as well. Remember this particular statement as well. Okay. Now, where do I use these statements? Let's try to solve one basic question so that it becomes clear to you. Have a look. Have a look, guys. Understand. As per this particular question is concerned, we are given with 2 gases in the container. One is O2, one is O3. We have got a mixture of 2 gases in the container. We have got a mixture of 2 gases in the container. Their mass ratio is given. Their mass ratio is given. What does that mean? That means WO2 divided by WO3. That's given to me as 4 by 3. That's given to me as 4 by 3. Right? Now, can I convert this mass ratio into molar ratio? Number of moles of O2 means mass of O2 divided by molar mass of O2. Number of moles of O3 means mass of O3, molar mass of O3. Right? WO2 divided by WO3, it's given to me as 4 by 3. MO3 is molar mass of O3 is 48 grams. Molar mass of O2 is 32. The value comes out to be 3:1, 3:16, 4:1, 4:8. The value comes out to be 2:1. So molar ratio I calculated. I was given with the mass ratio of the gases. I was given with the mass ratio of the gases. Yesterday, I attempted 24 questions of chemistry on JEE mains and all the questions are correct, sir. This is because of you. That's great. That's amazing. Keep on doing such things. Glad to know that. Glad to know that. Congrats. Okay. So, mass ratio was given, you got the molar ratio. Mass ratio was given, you got the molar ratio. Now, what am I supposed to calculate? I'm supposed to calculate vapor density of this mixture. I told you a few minutes back. Only. What is that? I told you molar mass of the mixture is equal to 2 times vapor density of the mixture. Or I can say vapor density of the mixture is equal to molar mass of the mixture divided by 2. Right? Simple. Okay. Vapor density of the mixture is equal to molar mass of the mixture divided by 2. Now the point is, how do we calculate molar mass of the mixture? See, these are the 2 gases which are given to us. Molar mass of the mixture would be simply M1N1 plus M2N2. This is the general formula. Divided by N1 plus N2. This is how you calculate molar mass of the mixture. And in the denominator, you have got 2. In the denominator, you have got 2. Now, M1 here is 32. M2 here is 48. And their molar ratio is 2:1. If their molar ratio is 2:1, That means let its moles are 2x. Let its moles be x. Okay, now we are done. M1 into N1. M1 into N1. 32 into 2 is 64x plus M2 N2. This comes out to be 48x divided by 2 into N1 plus N2. 2x plus x makes it 3x. Right? So x everywhere cancelled. So 64 plus 48 divided by 6. This is the final answer of the question. This is going to be the vapor density of the mixture. Is this clear, guys? Quickly in the chats. Let me know once in the chats if the concept of vapor density is clear. Let me know once in the chats if the concept of vapor density is clear. Okay? Simple. I use the formula and we did the question. Nothing else. No rocket science here. Now comes one more important concept. That is your limiting reagent. That is your limiting reagent. This is one important concept and you should know it properly. Okay? See guys, what is a limiting reagent first of all? Let me tell you, limiting reagent is nothing. It is that reactant which gets completely consumed. That reactant which gets completely consumed earlier in the reaction. That reactant which gets completely consumed earlier in the reaction is what you call as limiting reagent. See, you know, when the reaction starts, reactants keep on getting consumed. Reactants keep on getting consumed and products keep on getting formed. Now that particular reactant which gets completely consumed, that too earlier in the reaction, is what you call as limiting reagent. Is what you call as limiting reagent. And let me tell you, the other reactant, apart from the limiting reagent, the other reactant is what you call as the excessive reagent. It is called as the excessive reagent. It is called as the excessive reagent. It is called as the excessive reagent. It's called as the excessive reagent. Let me tell you, all the product formation is decided by the limiting reagent. Limiting reagent is the one that decides every single thing in the reaction. Decides every single thing in the reaction. Have a look how. My dear students, understand in it a very precise way, short way. Let's say you've got a reaction like this, 2 times A plus 3 times B. It gives 5 times C. Let's say this is the reaction. 2 times A plus 3 times B gives 5 times C. For example, I'm starting with, let's say I'm starting with 10 moles of A as well as 10 moles of B. So initially I've got 10 moles of A with us, 10 moles of B with us. Since the reaction has not started yet, so moles of C right now would be 0. Because the reaction has not started yet. I'm assuming reaction has not started. Now when the reaction starts, moles of A as well as moles of B, they'll keep on decreasing. Why? We know reactants keep on getting consumed with time. So moles of these reactants will keep on decreasing with time. And moles of product will keep on increasing with time. Moles of product will keep on increasing with time. Right? Moles of reactants will keep on decreasing with time. Moles of products will keep on increasing with time. Correct? Now, my dear students, I'll say when the reaction starts, moles of reactants are decreasing with time. Now, there will be one reactant which would be getting completely consumed in the reaction. Among these two reactants, there would be one reactant that gets completely consumed. That's your limiting reagent. How do you identify which one is the limiting reagent? What you need to do? Divide the given moles by the respective stoichiometric coefficients. Divide the given moles by the respective stoichiometric coefficients. The one that gets the lesser value, that's the limiting reagent. For example, 10 divided by 2. 10 by 2 is 5. 10 by 3 is 3.33. 10 by 2 is 5. 10 by 3 is 3.33. Which one is getting lesser value? B is getting lesser value. The one that gets the lesser value, that is your limiting, and the other one is going to be your excessive reagent. And people, if B is the limiting reagent, it would have got completely consumed in the reaction. After some time, there will be 0 moles of B left in the container. The container in which reaction is taking place, in that container, after some time, there would be 0 moles of B left because entire B would have got consumed. Now, all the things, see, when B would have got completely consumed, at that point of time, I would say reaction would have stopped. Reaction would have stopped at that time. When B would have got completely consumed, reaction would have stopped. Now, all the product formation is decided by the limiting reagent. All the product formation is decided by the limiting reagent. How exactly? Have a look. See, 3 moles of B, as per stoichiometry, should give 5 moles of C. 3 moles of B should give 5 moles of C. I'll write it for you. 3 moles of B should give 5 moles of C. Therefore, as per unitary method, 1 mole of B should give 5 by 3 moles of C. Right? 1 mole of B should give me these many moles of C. But how many moles of B we have? 10. So 10 moles of B should give 5 by 3 multiplied by 10. So it should give me 50 divided by 3 moles of C. So I would say at the end of the reaction, 50 divided by 3 moles of C would have got formed. Right? Perfect. Now similarly, what is this A? A is the excess reagent. That means out of 10 moles of A, there would be some moles of A which would be left in the container as such in the unreacted form. This has got completely consumed. Now, this is excessive. So out of 10 moles of A, some moles of A would be still left in the container as such. How do we get that? How do we get that? See guys, see first of all, that also is going to be decided by the limiting reagent. How? I can say 3 moles of B. I can say 3 moles of B reacts with 3 moles of B reacts with 2 moles of A. Stoichiometry is telling me that. 3 moles of B reacts with 2 moles of A. Therefore, 1 mole of B reacts with 2 by 3 moles of A. Okay. 1 mole of B reacts with 2 by 3 moles of A. So 10 moles of B would have reacted with 2 by 3 multiplied by 10. That means 40 divided by 3 moles of A. So I got to know one thing. What is that? I got to know 10 moles of B. I got to know 10 moles of B would have reacted with these many moles of A. How many moles of A I had taken? I had taken 10. I had taken 10 moles of A. Out of 10 moles of A, how many are reacting? These many moles of reacting. So how many moles of A would be left? Number of moles of A left in the container would be equal. How many I had taken? 10. How many are reacting? 40 by 3. Right? Did we do some mistake here? This is 20 by 3, sorry. This is 20 by 3. Right? This is 20 by 3. Okay? So it comes out to be finally 10 by 3. So I would say at the end of the reaction, 10 by 3 moles of A would be still left in the container as such. Am I clear with this? Say yes or no once in the chats quickly. Say yes or no once in the chats quickly, people. Perfect. Amazing. Let's try to do some questions so that you can understand it properly. 3 moles of NaOH. 4 moles of H2SO4. Find the limiting reagent. Tell me the answer in the chats, everybody. Quick. Which one is limiting? How do you understand the limiting? How do you identify the limiting reagent? Divide the given moles by the respective stoichiometric coefficient. 3 divided by 2. 3 divided by 2, that's 1.5. 4 divided by 1, that's 4. So which one is limiting? NaOH is limiting. NaOH is the limiting reagent, right? We are given with a balanced chemical equation like this: 6 times LiH plus 8 times BF3 gives 6 times LiBF4 plus B2H6. This is your reaction, a balanced chemical equation. As per the question is concerned, on starting with 2 moles each of reactants, how many moles of B2H6 will be formed? How many moles of B2H6 would be formed? Tell me one thing. Which one is limiting reagent among the two? 2 by 6, 2 by 8. This is getting lesser value, so BF3 is limiting. If BF3 is limiting, completely consumed. Now, entire things will be decided by the limiting reagent, right? Now, see, stoichiometric coefficient here is 8, here is 1. I would say 8 moles of limiting reagent gives 1 mole of B2H6. So 1 mole of limiting reagent gives 1 by 8 moles of B2H6. Therefore, 2 moles of limiting reagent gives into 2 moles of B2H6. So it comes out to be 1 by 4. So 0.25 moles of B2H6. So these many moles of B2H6 are formed. These many moles of B2H6 are formed. Done? Perfect. Got it? Got it, people? Okay, if I ask you how many moles of LiH are unused, unreacted, how many moles of LiH will be still left at the end of the reaction? When the reaction would have stopped, how many moles of LiH would be left? Say, that also will be decided by the limiting reagent. I'll say 8 moles of limiting reagent reacts with 6 moles of LiF. Therefore, 1 mole of limiting reagent reacts with 6 by 8 moles of LiF. Right? So 2 moles of limiting reagent reacts with 6 by 8 multiplied by 2. So 12 by 8. So 1.5 moles of LiF. So I would say out of 2 moles of LiH, is this LiF or LiH? LiH. Okay. This LiH. Okay, so we got to know 2 moles of BF3. 2 moles of BF3 are reacting with 1.5 moles of LiH. So how many would be left? I had taken 2. Out of 2, 1.5 is reacting. So 0.5 moles of LiH would be still left in the container as such. Am I clear with this? Am I clear with this, guys? So before starting the next topic, let's take a short break. But only at one cost I'm giving you the break. You are going to join me back. We have to end every single thing in the today's session. And our session is long. It's till 11. So don't worry. Okay, so it's 1:50 right now. I'm giving you the break till 2:20. But at 2:20, I would want every one of you to be back. Okay, go and have your lunch quickly and get back on time. Go get your lunch quickly and get back on time. Okay? Get your lunch quickly and get back on time. Are you all back? Welcome back, guys. Welcome back. So what's up? How are you all? Are you done with your lunch? Sir, do vapor density have units? No, vapor density is unitless. Vapor density is unitless. No, I did not have my lunch yet. I just had coffee. That's it. I'll have lunch when I'll give you the second break. Perfect. Should we start then? I think everyone is ready. Should we start? All right, let's get going with one more important topic, that is your percentage yield. Well, the questions are asked from this particular topic as well. In a reaction, you are supposed to calculate the percentage yield. So first of all, let me give you the result with the help of which you can calculate percentage yield of the reaction. Let me give you the result first, then I'll show you how the result is applied in the questions. So my dear students, if I talk about the percentage yield, percentage yield in a reaction is calculated by the formula, that is experimental or the actual amount, experimental or the actual amount divided by the expected or you call it as the theoretical amount multiplied by 100. This is first of all the result with the help of which we can calculate the percentage yield on the reaction. Now guys, few things which I would want you guys to remember. The experimental amount or the actual amount, this would be given to you in the question itself. Expected or theoretical amount we need to calculate with the help of stoichiometry. This is something which we need to calculate with the help of stoichiometry. Experimental actual amount will be given to you in the question. Expected amount we will have to calculate with the help of stoichiometry. And once we get experimental amount, expected amount, we just have to divide them and multiply with 100. We will be getting the percentage yield of the reaction. For example, let me make you understand this particular concept with the help of one simple question so that you can remember it. For example, you have got a question. The question says, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was obtained. Calculate the percentage yield of the reaction. My dear students, let me first of all write the reaction again. We have got calcium carbonate. We are heating it up. It gives calcium oxide. And with calcium oxide, you have got carbon dioxide. Now, in the question itself, they are telling us that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was produced. So basically, the data which is given to us, the data is saying 40 gram calcium carbonate upon heating produces 20 grams of calcium oxide, right? So this has been experimentally verified. This is experimentally checked in the lab itself that when we heat 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this amount over here is something which has been experimentally verified. So I'll be calling this particular amount as the experimental amount. This has been observed experimentally. Now, in order to calculate the yield of the reaction, how many amounts do I need? 2 amounts, experimental and expected. We already know the experimental amount, right? Now, what do I need? I need the expected amount. Expected amount is calculated with the help of what? Expected amount is calculated with the help of stoichiometry. Expected amount is calculated with the help of stoichiometry. Now, let me use the stoichiometry. Try to understand. First of all, the reaction is balanced. If I ask you, what is the mass of 1 mole of calcium carbonate? Mass of 1 mole of calcium carbonate means molar mass of calcium carbonate. How much is that? That is 100 grams. So let me write 100 grams of calcium carbonate on heating. What is the mass of 1 mole of calcium oxide? That will be its molar mass, which is 40 plus 16, that is 56 grams. So stoichiometry is telling me that 100 gram calcium carbonate upon heating should produce 56 grams of calcium oxide. This is stoichiometry telling me. This is all theoretical. This is all what we do on pen and paper. So stoichiometry is telling me that 100 gram calcium carbonate upon heating should produce 56 grams of calcium oxide. Therefore, 1 gram calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide, right? If 1 gram calcium carbonate should produce these many grams of calcium oxide, therefore 40 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 40 grams of calcium oxide. And when you solve this, this value approximately would come out to be I think 22.4 grams. So basically, if you look carefully, we used the term stoichiometry. From stoichiometry, we got to know that 40 gram calcium carbonate upon heating should produce these many grams of calcium oxide. So this is something which I was expecting. So this is my expected amount. This is my expected amount through stoichiometry. But how much calcium oxide actually is being formed in the lab? 20 grams. This is experimental, this is expected. If you know both the amounts, can't we calculate yield? Percentage yield is nothing. Experimental amount divided by expected amount multiplied by 100. The value comes out to be 89%. So the yield of this particular reaction is nothing but 89%, right? The efficiency of this reaction is 89%. How much I was expecting this calcium oxide to get formed? 22.4 grams. How much actually is being formed? Only 20 grams. So the yield of the reaction is less than 100. How much exactly? 89%. Am I clear with this? Yes or no in the chats quick? Yes or no in the chats quick? One more question. The question is, on heating 150 grams of calcium carbonate, what mass of calcium oxide is formed if the yield of the reaction is 75%? If the yield of the reaction is 75%. Understand. As per the question, we are heating 150 grams of calcium carbonate. And when calcium carbonate is heated, you know, it gives calcium oxide, and with that, you get carbon dioxide. Okay. Let's first of all do the stoichiometric calculation and check how much calcium oxide should have got formed. How much calcium oxide should have got formed? Let's use stoichiometry for that. First of all, reaction is balanced. 1 mole calcium carbonate. Its mass is 100 grams. Okay. 1 mole calcium oxide, its mass is 56 grams. So stoichiometry is telling me that 100 gram calcium carbonate upon heating should produce 56 grams of calcium oxide. Therefore, 1 gram of calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide, right? So I can say 150 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 150 grams of calcium oxide. So this is the amount of calcium oxide which I was expecting to get formed. But look at the yield of the reaction. Yield of the reaction is 75%. That means in the lab, this much amount of calcium oxide won't get formed. Then how much actual amount of calcium oxide would get formed? How much actual amount of calcium oxide would get formed? 75% of what you expected. Solve this, and this will give you the actual amount of calcium oxide which would be getting formed in the reaction. Am I clear with this? Am I clear with this, people? Let me know once quickly. Am I clear with this? Yes? Perfect. This is something which I was expecting to get formed, right? But the yield of the reaction is 75%. So 75% of this amount in reality would be getting formed. That is the actual amount of calcium oxide. I hope this is clear. Let's move on. Let's move on to something called as percentage purity. You might have seen this particular topic as well. Percentage purity. My dear students, how do we first of all define percentage purity? I would say percentage purity of a compound. Percentage purity of a compound in an impure sample. In an impure sample is defined as the mass of pure compound. It is defined as the mass of pure compound in grams present in 100 grams of impure sample. Present in 100 grams of impure sample. So in 100 grams of impure sample, how much mass of pure compound is present? How much mass of pure compound is present? For example, let's say this is your container. Let's say in this container I have got NaCl. With NaCl I have got some impurities as well, which I am representing with ABC. Okay, which I am representing with ABC. So first of all, this is the impure sample of NaCl. Let's assume the mass of the impure sample, the mass of the entire sample of NaCl is, for example, 500 grams. This is the mass of the entire impure sample. Let's say in 500 grams of this impure sample. Let's say in 500 grams of this impure sample, the mass of pure NaCl is, let's say, 10 grams. The mass of pure NaCl is 10 grams. Okay? The mass of pure NaCl is 10 grams. Now, can I say 500 grams of the impure sample contains 500 grams of the impure sample contains 10 grams of pure NaCl? 10 grams of pure NaCl? Yes, I can say that. Therefore, 1 gram of the impure sample contains 10 divided by 500 grams of pure NaCl. Right? Perfect. So I can say 100 grams of impure sample, as per the definition, 100 grams of impure sample will be containing 10 by 500 multiplied by 100 grams of pure NaCl, right? So 0000 cancel, 5152. So it comes out to be 2 grams of NaCl. So what we got to know? What we got to know? We got to know that 2 grams of pure NaCl, 2 grams of pure NaCl are present in 100 grams of impure sample. And that mass of pure compound, which is present in 100 grams of impure sample, what do I call this as? I call this as the percentage purity of NaCl in the sample. Perfect. So if I say percentage purity of NaCl in the sample is 2, what does that mean? That means 2 grams of pure NaCl are present in 100 grams of impure sample. If I say percentage purity of calcium carbonate in the sample is 40%, what does that mean? That means 40 grams of pure calcium carbonate is present in 100 grams of the impure sample. As simple as that. Okay. Now, my dear students, I'm giving you one result which you are going to remember from now onwards to calculate the percentage purity. I'll say percentage purity of a compound in an impure sample is equal to mass of the pure compound in grams, divided by the mass of impure sample multiplied by 100. This is the result with the help of which we can calculate the percentage purity of a compound in an impure sample. This is the result which I would want you guys to take a note of. Number 1. Number 2. For example, sometimes you'll find a statement in the questions like this. 80 grams of 40% pure calcium carbonate. Sometimes you'll find a statement like this. 80 grams of 40% pure calcium carbonate. What does it mean? It means that you have got a sample. You have got a sample of calcium carbonate. The mass of the entire sample is 80 grams. And out of 80 grams of sample, what is the mass of pure calcium carbonate? The mass of pure calcium carbonate would be 40% of 80. So 40 divided by 100 multiplied by 80. The value comes out to be 32 grams. So I would say if 80 grams is the mass of entire sample, in 80 grams, 32 grams would be the mass of pure calcium carbonate present. Okay. Sometimes, for example, if I write a statement like this, let's say I'm writing 70 grams of 20% pure NaCl. What does it mean? What does it mean? It means that you have got a sample of NaCl containing some impurities as well, right? What is the mass of that entire sample? The mass of that entire impure sample is 70 grams. Now, among 70 grams, what is the mass of pure NaCl? The mass of pure NaCl would be 20% of 70. The value comes out to be 14 grams. So 14 grams would be the mass of pure NaCl present in the sample. Am I clear with this? Next point. Do remember one more thing. Do remember, in a chemical reaction, only the pure substance participates. In a chemical reaction, only the pure substance participates. Only the pure substance participates. Remember that impurities do not participate in a chemical reaction. In a chemical reaction, it's only going to be the pure substance that's going to participate. Impurities are not going to participate in a chemical reaction. Let's try to solve a question with the help of which you'll understand this particular concept. See guys, look at this particular question. These sort of questions are asked. 50 grams of 80% pure calcium carbonate. 50 grams of 80% pure calcium carbonate is heated. calculate the volume of carbon dioxide gas produced. So first of all, if I ask you, what is this 50 grams? This is the mass of entire sample of calcium carbonate, right? In that entire sample of calcium carbonate, what is the pure mass of calcium carbonate? Pure mass of calcium carbonate would be 80 divided by 100 multiplied by 50. The value comes out to be 40 grams. So basically, we have got 40 grams of pure calcium carbonate, and we are heating the 40 grams of pure calcium carbonate. And we know when pure calcium carbonate is heated, what do we get? Calcium oxide. And with calcium oxide, what do we get? Carbon dioxide. Right? Now, my dear students, this is the pure mass of calcium carbonate, right? So how many pure moles of calcium carbonate we have? 40 divided by its molar mass. So these are the pure moles of calcium carbonate which we have. And in the reaction, only the pure substance participates. Impurities do not participate in the reaction. So in this reaction, I would say 0.4 moles of calcium carbonate are going to participate. Simple. So people, it's pretty much simple now. Have a look. Stoichiometry coefficient here is 1. Here is 1. Can I say, as per stoichiometry, 1 mole calcium carbonate on heating gives 1 mole carbon dioxide. 1 mole calcium carbonate on heating gives 1 mole carbon dioxide. Therefore 0.4 moles of calcium carbonate on heating should give 0.4 moles of carbon dioxide. So I got to know these are the moles of carbon dioxide which are being produced. But as per the question, do I need to calculate moles of carbon dioxide produced? No. I need to calculate volume of carbon dioxide produced, which is equal moles of carbon dioxide multiplied by 22.4 liters. The value comes out to be 8.96 liters. So I would say 8.96 liters of carbon dioxide would be produced. Am I clear with this? Say yes or no in the chats. Quickly. Am I clear with this concept? Just remember one thing, in a chemical reaction, only the pure substance participates. Impurities do not take part in a reaction. Impurities do not take part in the reaction. Perfect? All right. Let's have a look on one more question of the same manner so that you will understand it properly. Look at this question, guys. Look at this question. First of all, we are given with some reaction. Let me note the reaction again here. H2SO4 plus twice NaOH. What does it give us? It gives us Na2SO4 plus 2 times water. This is the reaction. Now the question says 5 grams of H2SO4 sample. 5 grams of H2SO4 sample. 5 grams of H2SO4 sample. So what is this 5 grams? 5 grams, I would say, is the mass of impure sample of H2SO4. This is the mass of impure sample of H2SO4. 5 grams of H2SO4 sample exactly requires 4 grams of NaOH. Exactly requires 4 grams of NaOH for neutralization. Calculate the percentage purity of H2SO4 in the sample. Right? See, percentage purity of H2SO4 in its sample as per the formula has to be equal to mass of pure H2SO4 in the sample divided by the mass of impure sample multiplied by 100. Well, this particular term already we have, that's 5 grams. What I need to calculate? I need to calculate the mass of pure H2SO4. I need to calculate the mass of pure H2SO4 in the sample. How do I get the mass of pure H2SO4? We know in a reaction only pure substance participates, right? So what I'll be doing, I will be using stoichiometry and I'll try to calculate how much H2SO4 has participated in this reaction. I'll try to calculate how much H2SO4 has participated in this reaction. And that much amount of H2SO4 which would have participated in this reaction would be called as pure mass of H2SO4. That's it. Okay? Now try to understand. Try to understand. What is the mass of 2 moles of NaOH? Mass of 2 moles of NaOH would be 80 grams. What is the mass of 1 mole H2SO4? That would be 98 grams. So can I say simply 80 grams of NaOH, 80 grams of NaOH requires 98 grams of H2SO4 as per stoichiometry. Therefore, 1 gram of NaOH reacts with 98 divided by 80 grams of H2SO4. Correct? Now 4 grams of NaOH reacts with, I would say, 4.9 grams of H2SO4. So I would say, I got to know from stoichiometry, 4 grams of NaOH are reacting with 4.9 grams of H2SO4. So this is the mass of H2SO4 which is participating in the reaction. This is the mass of H2SO4 which is participating in the reaction. And that mass of H2SO4 which participates in the reaction is going to be the pure mass. This is the pure mass of H2SO4. So we are done. So I'll say percentage purity of H2SO4 in the sample has to be equal. Mass of pure H2SO4, 4.9. Mass of impure sample, 5 grams multiplied by 100. The value comes out to be 98%. Right? So in the sample of H2SO4, you had taken 5 grams of H2SO4 sample. So in the sample, there was H2SO4 with impurities. And the mass of entire sample was 5 grams. And in that sample, percentage purity of H2SO4 is 98%. That means 98 grams of pure H2SO4 would be present in 100 grams of that particular impure sample. If I'm clear, let me know once in the chats quickly. If I'm clear, let me know once in the chats quickly, guys. If I'm clear, let me know once in the chats quickly. Perfect. Great. Now, guys, this is one more sort of question that you would have seen maybe in your books or somewhere, right? Let's see how do we deal with this sort of a question. Let's say how do we deal with this sort of a question. The question is, understand properly. The question is, we have got a container. In this container, what do we have? We have got magnesium and aluminum present in this container, right? Well, this is an alloy. It is an alloy of magnesium and aluminum. As per the question, the mass of this alloy, the mass of this mixture is nothing but 1 gram. The mass of this mixture is nothing but 1 gram. Okay? So 1 gram is the mass of the entire mixture. Now, first of all, let me assume from the 1 gram of the mixture, let's say there are X grams of magnesium present in the container. So remaining 1 minus X grams would be the mass of aluminum. Correct? So if I ask you, first of all, how many moles of magnesium are there in the container? Mass of magnesium divided by molar mass of magnesium. Mass of aluminum divided by molar mass of aluminum. So I would say these are the moles of magnesium and aluminum in the mixture. These are the moles of magnesium and aluminum in the mixture, right? Now, as per the question, what are we doing? As per the question, in this mixture, we are adding HCl. In this mixture, we are adding HCl. So what is going to happen? The HCl which we are adding, can I say some part of HCl would be reacting with magnesium and some part of HCl would be reacting with aluminum, right? So how many reactions would be happening here? I would say 2 reactions would be happening in the container. I would say 2 reactions would be happening in the container, right? What is going to be the first reaction? First reaction is going to be magnesium reacting with HCl, and second reaction is going to be aluminum reacting with HCl. And you should know, when magnesium reacts with HCl, it forms MgCl2. With this, H2 gas is produced. When aluminum reacts with HCl, it forms AlCl3. With this also, H2 gas is produced. Right? This is something which we know. Now, just try to balance the reactions. Make this 2 times. Make this 2 times. Or wait. No, it's balanced. Mg plus 2 times HCl gives MgCl2. It's balanced. Now, we are supposed to balance this particular reaction. So how do we balance it? If I make it 3 times, so I have to make it 3 divided by 2 times. Both the reactions are balanced. So these are the 2 reactions which are happening here. The question says, when HCl is added in this container, 1.12 liters of H2 gas is produced. 1.12 liters of H2 gas is produced. So can you tell me how many moles of H2 gas are produced in total? It would be 1.12 divided by 22.4. I would say these are the total moles of H2 which are produced when this HCl is poured in the container. Right? Now these total moles of H2 which are produced, can I say, since these are the total moles of H2 which are produced as per the question, can I say some moles of H2 would be coming from this reaction? Some moles of H2 would be produced from this reaction. I'll say both these reactions will be contributing towards the generation, towards the production of H2. Simple. So, what I'll be doing, I'll be using stoichiometry. Understand? Coefficient here is 1, here it's 1. I'll first of all say 1 mole magnesium when reacts with HCl, it produces 1 mole H2. Therefore, in the container, do we have 1 mole of magnesium to react for? No. We have got X by 24. So I would say when X by 24 moles of magnesium would have reacted with HCl, I would say X by 24 moles of H2 would have produced. Correct? So these are the moles of H2 produced from reaction number 1. Right, people? Similarly, look at the second reaction. See, I will say when 1 mole aluminium reacts with HCl, 3 by 2 moles of H2 are produced. 3 by 2 moles of H2 are produced. But in the container, do we have 1 mole of aluminium to react with? No, there is 1 minus X by 27. So I would say when 1 minus X divided by 27 moles of aluminium reacts with HCl, I would say 3 by 2 multiplied by 1 minus X by 27 moles of H2 is produced. Okay, right? So I got to know the moles of H2 produced from second reaction, moles of H2 produced from first reaction. So I can simply use a concept. Number of moles of H2 produced from reaction number 1 plus number of moles of H2 produced from reaction number 2 has to be equal to total moles of H2 produced. Has to be equal to total moles of H2 produced. Right? Perfect. Now people tell me, how many moles of H2 are produced from reaction number 1? X by 24. How many moles of H2 are produced from reaction number 2? 3 by 2 multiplied by 1 minus X by 27 is equal. How many moles of H2 are produced in total? It's 1.12 divided by 22.4. Look at this particular equation. In this particular equation, there is only one unknown X. Just solve it and get the value of X. And get the value of X. What was this X? X was the mass of magnesium in the container. If you got X, you can calculate the mass of aluminum in the container as well. That is something which I was supposed to calculate. Nothing more than that. Did you understand? Did you understand this question? This sort of a question can be also asked. This sort of a question can also be asked. Similar sort of question I'll show. Similar sort of question I'll show you. Look at this one. A similar sort of question. Look at this one. Understand, guys. As far as this particular question is concerned, a gaseous mixture of propane and butane. So we have got a gaseous mixture containing propane and butane. Propane is your C3H8. Butane is C4H10. A gaseous mixture containing propane and butane of volume 3 liters. Mass of the entire mixture is 3 liters. Mass of the entire mixture is 3 liters, right? So first thing that I'll assume, let's say from these 3 liters, we have got, we have got, let's say, X liters of propane in the container. Remaining is going to be 3 minus X liters. That's going to be the volume of butane in the container. Now, as per the question, we are doing the combustion of this mixture. We are doing the combustion of this mixture. Combustion of this mixture means we are doing the addition of oxygen. We are doing the addition of oxygen. Can I say the oxygen which we are adding, some part of the oxygen added would be reacting with this, and some part of the oxygen added would be reacting with this. So total how many reactions would be happening here again? Again, two reactions would be happening. The first reaction, your propane would be reacting with oxygen. Second reaction, your butane would be reacting with oxygen too. And combustion of hydrocarbon leads to the formation of carbon dioxide. And with carbon dioxide, you'll be getting water as well. With carbon dioxide, you'll be getting water as well. So two reactions are happening here, due to which carbon dioxide is being formed, right? Look at the question carefully. The question says, when this entire mixture undergoes combustion, 10 liters of carbon dioxide in total is produced. So volume of carbon dioxide produced in total, as per the question, is 10 liters. And we got to know these 10 liters are basically somewhat produced from this reaction as well as this reaction. So both the reactions are contributing towards the generation of the 10 liters of carbon dioxide. I would say some of the liters of carbon dioxide would be released from reaction number 1. Some of the liters of carbon dioxide would be liberated from reaction number 2. So let's get to know how much. Understand carefully. Let's try to balance the reaction. This should be 3 times. This should be 4 times. This should be 5 times. Similarly, this should be 4 times. This should be 5 times. This should be 13 by 2 times. I've shown you already how do we balance these sort of reactions. Now, understand carefully. Stoichiometry coefficient here is 1, here is 3. I would say from the stoichiometry, when 1 liter propane undergoes combustion, 3 liters of carbon dioxide are produced. When 1 liter propane undergoes combustion, 3 liters of carbon dioxide are produced. Correct? But in the container, did we have 1 liter of propane for the combustion? No, we had X liters. So I would say when X liters of propane would undergo combustion, 3X liters of carbon dioxide would be getting produced. So this is the volume of carbon dioxide is being produced from reaction number 1. Similarly, from reaction number 2, coefficient here is 1, here is 4. Stoichiometry is telling us that 1 liter butane, when undergoes combustion, 4 liter carbon dioxide is produced. 1 liter butane, when undergoes combustion, 4 liter carbon dioxide is produced. But in the container, we did not have only 1 liter of butane. We had 3 minus X. So when 3 minus X liter butane undergoes combustion, I would say 4 multiplied by 3 minus X liters of carbon dioxide gas would be getting produced. So this is the volume of carbon dioxide produced from reaction number 2. Okay. So I'll use the concept. Volume of carbon dioxide produced from reaction number 1 plus volume of carbon dioxide produced from reaction number 2 has to be equal to the total volume of carbon dioxide produced. From reaction number 1, 3x. From reaction number 2, 4 into 3 minus 6. Total 10 liters. So 3x plus 12 minus 4x is equal to 10. So the value of x comes out to be 2 liters. So x means in this particular container, there were 2 liters of propane and 3 minus 2 is 1 liter of butane, which is something I was supposed to calculate. Am I clear with this particular concept? Say yes or no in the chats quick. Say yes or no in the chats quick. Am I clear with this concept? Am I clear with this? All right. Perfect. Now comes the easiest topic of this chapter, right? And it's a short topic from which questions are frequently asked. That is empirical and molecular formula, and this is going to be our last topic of the chapter, mole concept. Okay. See guys, understand. What is empirical formula and what is molecular formula? See, let me not write the definition and stuff. I'll just give you the examples and you'll understand it. You'll understand it. I know all of you love this topic, but I hate it. Yeah. See, first of all, let's say I'm writing C6H12O6. What is it? It's glucose. C6H12O6. It's glucose. In this glucose, how many elements do we have? We have 3 elements: carbon, hydrogen, oxygen. Right? Carbon, hydrogen, oxygen. What is the molar ratio of these elements here? I'll say 6:12:6. This is the ratio of the atoms. 6:12:6. Can we tell me, can we further simplify this ratio? Can we simplify this ratio? Yes, we can further simplify this ratio. It can become 1:2:1. Okay? This particular ratio, 1:2:1, what do I call this as? This is the simplest whole number ratio, right? And this particular ratio, I would be calling this as actual ratio. One is the simplest whole number ratio, one is the actual ratio. As per the simplest whole number ratio, what should be the formula? Formula should be C1H2O1. So I have mentioned 2 formulas here. One formula is giving me simplest whole number ratio, one formula is giving me actual ratio. That formula which gives me simplest whole number ratio is what I call as empirical formula. That formula which gives me the actual ratio of the atoms, that's what I'll be calling as molecular formula. That's what I'll be calling as molecular formula. So I've got 2 formulas here. One is empirical formula, one is molecular formula. Empirical formula gives me the simplest whole number ratio. Molecular formula gives me the actual ratio. Okay? Now guys, one more thing. With the help of molecular formula, we can calculate molecular mass of a compound. And with the help of empirical formula, we can calculate empirical mass of the compound. With the help of molecular formula, molecular mass of the compound is calculated. With the help of empirical formula, I would say empirical mass of the compound is calculated. Now, molecular mass is equal. Use the molecular formula. 12 into 6 plus 1 into 12 plus 16 into 6. That comes out to be 180 U. This is the molecular mass of the compound. Now calculate the empirical mass. 12 into 1 plus 1 into 2 plus 16 into 1. That comes out to be 30 U. So I got molecular mass as well as empirical mass. After getting molecular and empirical mass, I'll be introducing a term N. This N does not represent moles here. It's a number N. You can represent it with X, Y, Z. I'm representing it with N. What is N? N is nothing but it is the ratio of molecular mass of the substance to that of empirical mass of the substance. N is the ratio of molecular mass of the substance to that of empirical mass of the substance. Now, for example, I'm asking you, what is the N value for glucose? What is the N value for glucose? Molecular mass, 180 U. Empirical mass, 30 U. The value comes out to be 6. So, N value for glucose is 6. N value for glucose is 6. Now, people try to understand one more thing. There is one more formula which you must know. Molecular formula of a compound is always equal to empirical formula multiplied by N. Molecular formula is always equal to empirical formula multiplied by N. You can check it out also, whether this formula is right or wrong. For example, glucose. What is the molecular formula of glucose? C6H12O6. What is the empirical formula of glucose? C1H2O1. Multiply with N. N value is 6. So 6 ones are 6, 6 to 12, 6 1 6. LHS RHS is equal. So this formula is valid. It's correct. It is correct. Do you understand this? One more thing which I'll be using in the questions. What is that? Remember, your molar mass is equal to 2 times the vapor density, which we have already, this result we have discussed. It is just, I want you guys to remember, because in the questions of molecular empirical formula, this result is used. Okay? This result is used. Now, my dear students, the first point is, how do we calculate molecular formula? Right? That is the first thing. How do we calculate the molecular formula? Empirical formula. That's the first thing. Once we get the empirical formula, we can easily calculate molecular formula through this result. Now try to understand what exactly we are going to do. Try to understand what exactly we are going to do. Let me show you the answer directly. Understand and remember these points. What exactly I'm going to show. Okay, remember them directly. Remember the process. The process is pretty much simple. We have got a compound that contains 3 elements. Compound contains potassium, chromium, and oxygen. We have got a compound that contains how many elements? 3 elements. Potassium, chromium, oxygen. As per the question, the mass percentage of potassium is given, the mass percentage of chromium is given, the mass percentage of oxygen is given. Mass percentage of all these elements is given to us. What does that mean? What is meant by 26.6? See, we have got a compound. Compound contains how many elements? Compound contains 3 elements. Potassium, chromium, oxygen. Mass percentage of potassium is given. It means that 26.6 grams of potassium are present in 100 grams of compound. 35.4 grams of chromium are present in 100 grams of compound. 38.1 grams of oxygen are present in 100 grams of compound. This is what you call as mass percentage, right? So in the question, mass percentage of all the elements is given. Now let me tell you one more thing. Either in the question you will be given with mass percentage, or you will directly be given with the masses of the elements. Let's say 26.6 grams, here 35.4 grams, 38.1 grams. Either mass percentage would be given, or directly the mass of the elements would be given, or in the question you would be given with the mass ratio of elements. So out of these 3 terms, anyone can be given. Mass percentage, directly the masses, or the mass ratio of the elements, right? Among these 3 terms, one will be given to us. The first step always is going to be. What is that? Whatever masses are given to you, whatever mass percentages are given to you, whatever mass ratios are given to you, directly you need to divide them with the atomic mass of the element. For example, potassium's mass percentage is given. Divide this 26.6 with the atomic mass of potassium, that is 39. Divide this 35.4 with the atomic mass of chromium, that is 52. Divide this with the atomic mass of oxygen, that is 16. So you will be getting certain numbers over here. Right? And this is something which I call as atomic ratio. So what did we calculate? We calculated atomic ratio here. Once you get the atomic ratio, select the least number among the all. Select the least number. Which one is the least number? 0.68. So divide all of them with the least number. Dividing all of them with the least number. You got 1, you got 3.5. Right? So basically, if this was atomic ratio, this is what I'll be calling as the least atomic ratio. But is this least atomic ratio? Should I be calling it just as the least atomic ratio? Or this is the whole number ratio as well? This is not the whole number ratio yet. Because here you have got 3.5. It's not the whole number ratio. What do we need? We need the actual whole number ratio. How do I convert this into whole number ratio? Simple. This 3.5 you have to convert into whole number. So I'll be multiplying this with 2. Similarly this with 2. Similarly this with 2. So this becomes 2. This becomes 2. This becomes 7. Right? So in the compound you have got potassium. You have got chromium. You have got oxygen. And the simplest whole number ratio came out to be 2:7. This is the simplest whole number ratio, right? This is the simplest whole number ratio. So as per this simplest whole number ratio, the formula should be K2Cr2O7. And this particular formula, I would be calling as the empirical formula. Did you remember the process? I just want to know that. Did you remember the process? What is the process? What is the first step? What is the first step? First step is you will be either given mass percentage, mass ratio, or the masses directly, right? Divide them with their atomic masses. Once you are done with that, you will be getting atomic ratio. Divide the atomic ratio by the least number. You will be getting what? You will be getting the simplest ratio, right? Then eventually you need to convert that into whole number ratio. You will be getting the empirical formula. Okay, let me give you one more question so that you can remember it from now onwards. Let me give you one more question. Okay, one simple question this is. A compound of nitrogen and oxygen, a compound of nitrogen and oxygen was found to contain, you have got a compound containing these two elements, was to contain 7:16 by mass, nitrogen and oxygen. So mass ratio of elements is given. How much it is? It is 7:16, I think. Mass ratio. Calculate the molecular formula of the compound if vapor density of the compound is 46. We have to calculate molecular formula. For molecular formula, what do I need? For molecular formula, we need empirical formula. For molecular formula, we need empirical formula. How do I get the empirical formula? Understand. First thing, I'll be getting the atomic ratio. Atomic ratio how? 7 divided by atomic mass, 16 divided by atomic mass. The value comes out to be 0.5, value comes out to be 1. Okay? This is the atomic ratio. What about the least atomic ratio? See, select the least number among these two. 0.5. Divide every term with 0.5. 0.5 divided by 0.5. This would be 1 divided by 0.5. This value comes out to be 1. This value comes out to be 2. One value comes out to be 1. Second value comes out to be 2. So, I got the ratio between nitrogen and oxygen as 1:2. Is the simplest whole number ratio? Yes, it's simplest whole number ratio. So, formula as per this should be N1O2. I'll be calling this as the empirical formula. So, I've calculated the empirical formula. But what do I need? I need the molecular formula. What is molecular formula? Molecular formula means empirical formula multiplied by N. Empirical formula I got. What do I need now? I need N. I need N. Right? How do we get the N? N is nothing but N is molecular mass divided by empirical mass. Molecular mass is going to be 2 times vapor density. Vapor density is given. 2 times vapor density will give you that. So 46 into 2 is 92 divided by empirical mass. You can calculate with the help of empirical formula. So 14 plus 32 is 46. So empirical mass is 46. So N value here comes out to be 2. If N value comes out to be 2, so it is going to be N1O2 multiplied by 2. It comes out to be finally N2O4. So this is the molecular formula of the compound which I was supposed to calculate. Am I clear with this? Am I clear with this? Quick. Did you understand? Am I clear with this? Did you understand? Best time to finish the syllabus is this ending January only, or maximum 15th Feb. That is the ideal time of completing the syllabus. After that, only revisions. Is it clear, guys? Perfect. So I think these sort of questions, these are all the similar type of questions. Okay, you have got a compound containing 3 elements, right? Molar mass is given. Molecular formula you have to check. So calculate the empirical formula first, then automatically follow the same process. So these sort of questions you can easily do. I believe in that. Okay. So I think we should start the next chapter now. Next chapter is going to be the redox reaction. Next chapter is going to be the redox reaction. Am I clear with this? Is this particular chapter clear? Tell me in the chats quickly. Notes I'll be sharing in the Telegram. Mixture analysis questions I already showed you. That aluminium, magnesium, right? Similarly, butane, propane. Those are mixture analysis questions only. Those are mixture analysis questions only. All right. Just give me some 5 to 7 minutes. I'll be back, okay? You be here only. Just be here only. Give me 5 to 7 minutes. I'll be back. Then we'll be starting the redox reaction. Give me 5 to 7 minutes. I'll be back. All right, everyone is here? Everyone is here? So now we are going to start the new chapter that's going to be your redox reaction. Tell me first of all in the chats, have you studied this particular chapter before? Have you studied this particular chapter before? You can say honestly with a yes or no. आपसे ही 4 बार, huh? 4 times you have studied the same chapter from me, huh? Okay, got it. Chalo then, let's start the chapter. Redox reaction. My dear students, the first topic here in the redox reaction, you must be familiar about that. That is the oxidation state. That is your oxidation state. First of all, how do we define the term oxidation state? How exactly do we define the term oxidation state? See guys, oxidation state, it is simply defined as the charge present on an atom of an element. The charge present on an atom of an element in a given compound. In a given compound. Point number 1. What is meant by this? You'll get the idea in some time. First of all, take a note down. Take down these points. The second point here is the charge can be real or virtual. The charge can be real or virtual. In case of ionic compounds, the charge is real. And in case of covalent compounds, the charge is virtual. Let's try to understand every single statement in detail and try to understand what this oxidation state exactly is all about. See guys, for example, I'm taking an ionic compound. Let's say I'm taking an ionic compound. Which ionic compound exactly am I taking? See, the most common example of the ionic compound is your NaCl. So let me take NaCl over here. It is the typical example of the ionic compound, NaCl. Now, first of all, in case of your NaCl, you must be familiar with the fact sodium is a metal basically. Chlorine is a non-metal. Sodium is a metal, chlorine is a non-metal. If sodium is a metal, that means it has got the tendency to lose electrons. Chlorine being the non-metal, it has got the tendency to gain electrons. Now, what sodium is going to do, I would say sodium will lose its outermost electron and get converted into Na positive. And chlorine at the same time will gain this particular electron and will get converted into Cl negative. So what is happening here? I would say formation of cation and formation of anion has taken place. Right? So, since cation and anion has got formed, now between this cation and anion, there would be electrostatic force of attraction. And this electrostatic force of attraction is what you call as ionic bond. And that particular compound in which ionic bond is present, you call that compound as the ionic compound, right? So NaCl, it is your ionic compound. Now, my dear students, tell me just one thing. In case of ionic compound, in case of this NaCl, sodium exists as Na positive here. Chlorine is basically existing as Cl negative. Over here, basically, you have Na positive and Cl negative. Now, tell me one thing. Do you see any charge present on sodium? I would say one atom of sodium is carrying +1 charge. And one atom of chlorine is carrying -1 charge. The charge present on an atom of an element, is what you call as oxidation state. So I would say oxidation state of chlorine here is -1 and oxidation state of sodium here is +1. As simple as that. Oxidation state of sodium here is +1, oxidation state of chlorine is -1. That means one atom of sodium carries +1 charge, one atom of chlorine carries -1 charge. Okay? At the same time, do you see sodium is losing its electron completely and chlorine is gaining that electron completely? So I would say during the formation of ionic compound, complete loss and gain of electrons is taking place. Complete loss and gain of electrons is taking place. And due to the complete loss and gain of electrons, whatever charges arrive on the atoms, they are going to be your real charge. Okay, so due to the complete loss and gain of electrons, the charges arising on the atoms, they are your real charges. So this +1 indicates that sodium has lost its electron completely. This -1 indicates that chlorine has gained the 1 electron completely. Okay, so in case of ionic compounds, the charges are real. Perfect. Now, if I talk about the covalent compound, let me take the example of your covalent compounds. First of all, imagine that I've got a covalent compound AB. Let's say this is one of the covalent compound AB, right? I'm assuming that B is more electronegative than that of A. Now you tell me one thing. If B is more electronegative than A, I would say this bond pair would be shifted towards B. And when the bond pair gets shifted towards B, the electron density will increase. And that increase in the electron density is shown by delta negative here. Towards A, electron density is increasing and towards A, electron density is decreasing, and that decrease in electron density is shown by delta positive. Right? Towards B, electron density is increasing. Towards A, electron density is decreasing. So tell me one thing. In this particular covalent compound, is there complete loss and gain of electrons happening? No. I would say there's a shifting of electron pair. And due to the shifting of electron pairs, whatever charges come on the atoms, they are always your virtual charges. So first of all, what is the charge on this A? I would say +1. Charge on B is -1, right? Which is what I'll be calling as their oxidation states. But are these oxidation states, are they real charges or virtual charges? I'll say they are the virtual charges because they arise on the atoms due to the shifting of electron pair, not due to the complete loss and gain of electrons. Okay? For example, you have got a double bond between A and B. Again, I'm assuming B is more electronegative than that of A. If B is more electronegative than that of A, I'll say both these bond pairs will be shifted towards B, due to which this B gets 2 times delta negative, A gets 2 times delta positive. So if I ask you, what is the oxidation state of A here? You'll say +2. What is the oxidation state of B here? You'll say -2. Right? Sorry. Now at the same time, if I ask you, are these real charges or virtual charges? Your answer is going to be, these are the virtual charges present on the atoms. Right? Because there has not been the complete loss and gain of electrons happening here. Okay? In the similar way, guys, I'm pretty much sure you can conclude this one too. A triple bond B. If B is more electronegative, then -3 delta. This would be +3 delta. This oxidation state will be +3. This oxidation state would be -3. Okay? And few more things. Few more things, some general information which you should be knowing here. What is that? If I ask you in your periodic table, which element is considered to be maximum electronegative? It's fluorine, followed by oxygen, followed by nitrogen. This is something which you should know. At the same time, when you move from left to right in the periodic table, what happens to electronegativity? Electronegativity increases when you move from left to right in the periodic table. On moving from top to the bottom, what happens to electronegativity? Electronegativity decreases. Perfect. This is something which I believe every one of you knows already. Now comes the point. The point is, what are the rules to calculate the oxidation state? What are the rules to calculate the oxidation state? Rules to calculate the oxidation state. They are important and remember them directly. Okay? Rules to calculate oxidation state. Just a second. Okay. Rules to calculate the oxidation state. See guys, the first rule if I talk about oxidation state of an element. Oxidation state of an element in elemental, or I would say native state. Is taken as zero. For example, hydrogen in nature exists as H2 gas. Chlorine in nature exists as Cl2 gas. Right? Fluorine in nature exists as F2 gas. Okay? Iron in nature exists as Fe solid. Copper exists as copper solid. Okay? These are basically your elemental states. These are the native states of these elements. And whenever element is present in its native state, its oxidation state would be taken as zero. This is rule number one. Rule number two. Your group first elements. They show always the oxidation state of +1. And your group second elements, your alkaline earth metals, they show the oxidation state of +2. Group 1 and group 2, they are going to show the oxidation state of +1 and +2 respectively. Remember this particular point as well. The third point is particularly for hydrogen. Now understand. First of all, when hydrogen is present in its native state, its oxidation state is taken as zero. That means H2 gas, oxidation state is zero. But remember, when hydrogen would be present in the bonded form, when hydrogen will be attached with the element which is going to be more electronegative element than hydrogen. If hydrogen is attached to more electronegative element than itself, then let me tell you, oxidation state of hydrogen is taken as +1. Similarly, when hydrogen is attached with the less electronegative element than itself, I would say its oxidation state would be taken as -1. Okay? Similarly, if I talk about your oxygen, in case of oxygen, the first point, when oxygen would be present in its native state, elemental state, its oxidation state would be taken as zero. Point number one. Okay. When oxygen would be attached with less electronegative element than itself, generally oxygen is going to show -2 oxidation state. For example, you have got MgO, oxygen attached to an element which is less electronegative element than it, -2. For example, water, oxygen attached with less electronegative, so -2, right? Let's say you have got Cl2O, oxygen attached with less electronegative element than it. So minus 2. Okay. Similarly, oxygen forms some special compounds as well. You must have heard. Peroxides. That means when you see oxygen in this form, O2 dinegative form, whenever you see oxygen present in this particular format, O2 dinegative form, that means oxygen is forming the peroxide, and when oxygen forms the peroxide, its oxidation state is taken as -1. For example, talk about hydrogen peroxide, H2O2. All of you must be familiar with the structure of H2O2. This is your H2O2, right? Now, my dear students, if I ask you, this bond is between oxygen and hydrogen. Which one is more electronegative? Oxygen. So this bond pair will be shifted towards oxygen, so -1, +1. This bond pair will be shifted towards oxygen, -1, +1. And nothing happens to this particular bond because on one side oxygen, on other side also oxygen. So what is the charge present on one oxygen atom? -1. I would say oxidation state of oxygen when it forms your peroxide, H2O2, is what? -1. And this single bonded linkage between two oxygen atoms, O single bond oxygen, O single bond O, single bonded linkage between two oxygen atoms is what you call as peroxide linkage. This linkage here is what you would be calling as the peroxide linkage. And in any compound, if peroxide linkage is present, that means oxygen is forming peroxide, where its oxidation state would be taken as -1. Now, similarly, oxygen, it forms some other compounds too. Oxygen forms superoxides as well. Oxygen forms superoxides as well, right? When you see oxygen in this format, O2 negative format, when you see oxygen in this format, O2 negative format, okay? When oxygen is present in this format, we at that point of time say oxygen is forming superoxide, and when oxygen forms superoxide, its oxidation state is taken as -1/2. Similarly, oxygen forms some special compounds as well, which are what we call as oxyfluorides. And in case of oxyfluorides, oxidation state of oxygen is +1, +2. For example, you have got OF2 and you have got O2F2. Now understand, in OF2 and O2F2, what are the oxidation states? You can easily do it. See, this is a single bond between oxygen and fluorine. Which one is more electronegative? Fluorine. So this electron pair will be shifted towards fluorine, -1, +1. This electron pair shifted towards fluorine, -1, +1. So what is the charge on this oxygen here? I would say +2. Similarly, this is a single bond between oxygen and fluorine, -1 and +1. Single bond, -1, +1. In between, on one side oxygen, on another side oxygen. Nothing is going to happen. So charge present on one oxygen atom is +1. So I would say its oxidation state here is +1 in case of O2F2. Similarly, oxygen can form ozonoid as well. Whenever you see oxygen present in this format, O3 negative. Whenever you see oxygen present in this format, O3 negative, at that point of time, we say oxygen has formed ozonide, and its oxidation state here at this particular point of time will be taken as -1/3. These are some important things to be remembered about which element? About oxygen. Okay, so this was my rule number 1, 2, 3, 4. So this was my rule number 4. Now coming to rule number 5. Rule number 5 is particularly for halogens. First of all, halogens in their native states, standard states, elemental states, their oxidation state would be taken as 0. That's understood. And when a halogen is attached to less electronegative element than itself, oxidation state of halogen is taken as -1. When attached to less electronegative element, right? One more important thing, I would say halogens can show positive oxidation states as well. Halogens can show positive oxidation states as well. For example, I gave you a compound few minutes back, that was your Cl2. Let's say you have got BrF3. Let's say you have got IF7. I'm underlining certain elements here. And I want you to calculate the oxidation states of these elements. It's very simple. See, Cl2, this oxygen, chlorine and chlorine. BrF3, let me make its rough structure, not the actual structure. The actual structure we have discussed in bonding. I'm just attaching 3 fluorine atoms with it, right? Similarly, iodine, attach some 7, 1, 2, 3, 4, 5, 6, 7, 7 fluorine atoms with it. The rough structure I'm making. Now, first of all, in these cases, if you look carefully, this is the bond between oxygen and chlorine. Which one is more electronegative? Oxygen. So this bond pair shifts towards oxygen, so -1 and +1. This bond pair shifts towards oxygen, -1, +1. What is the charge present on one chlorine here? The charge present on one chlorine atom is +1. So I would say oxidation state of chlorine here is +1. Similarly, in case of bromine here, it would be +3 because 3 fluorine atoms. Iodine, +7. So halogens can show positive oxidation states as well as in case of these interhalogens. This is an interhalogen compound. This is also an interhalogen compound. Interhalogen means when 2 different halogens form a compound. Right? The compound formed by 2 different halogens is what we call as interhalogen. I hope this is clear. I hope this particular point is clear. Okay? Am I clear with this? Perfect, people. All clear? Now comes few more points. See, if you talk about your P block elements, P block elements, they show a range of oxidation states. Okay? And oxidation state of P block elements is between group number -18 to group number -10. Group number -18 to group number -10. For example, let's say I'm taking nitrogen, which is a P block element, right? I'm taking oxygen, which is a P block element, right? Let me take chlorine, which is a P block element. Do you remember their group numbers? It belongs to 15th group. This belongs to 16th group. This belongs to 17th group. So what is the range of oxidation states that nitrogen can show? 15 minus 18 is -3. 15 minus 10 is +5. Oxygen. 16 minus 18 is -2. 16 minus 10 is +6. Chlorine. 17 minus 18 is -1. And 17 minus 10 is +7. These are the range of oxidation states which your P block elements show. Okay? Which your P block elements show. Perfect. Now guys, one more thing I would want you guys to remember, that is about iron, chromium and manganese. Iron, chromium and manganese. These are your D block elements, right? Something you have to remember about them as well, because questions will be asked about these as well. Okay? Leave iron aside, only 2. One is chromium, one is manganese. Questions can be framed from these 2. See, maximum oxidation state shown by chromium is +6. Maximum oxidation state shown by manganese is +7. Just remember these 2 things. Okay, that is more than sufficient when it comes to your redox. Okay. Now similarly, my dear students, one more important rule which you must know. What is that? That is related to coordinate bond. Let's say there's a coordinate bond between A and B. A is the donor atom. B is the acceptor atom. Let's say there's a coordinate bond between A and B. A is donor, B is acceptor. Right? Now people, remember, if electronegativity of donor is less than that of electronegativity of acceptor, at that point of time, the donor gets +2 oxidation state, acceptor gets -2 oxidation state. Okay? Remember at the same time, if electronegativity of donor is greater than that of electronegativity of acceptor, if donor's electronegativity is more than that of acceptor's electronegativity, at that point of time, you won't be considering any charge on these atoms. Okay? At that point of time, you won't be considering any charge on these atoms. I hope this also clear. I hope this also clear. Correct? Now comes one more important point about the rules. What is that? The next rule is the sum of oxidation states. The sum of oxidation states of all the elements. The sum of oxidation states of all the elements in a molecule is equal to the net charge present on the molecule. Is equal to the net charge present on the molecule. What does it mean? Understand properly what I'll be saying, because this is something which is okay. See, this is something which I'll be using everywhere. Understand what I'll be saying, guys. For example, you have got MnO4 negative. Let's say you have got Cr2O7 dinegative. Let's say you have got NH4 positive. Let's say you have got S2O4 dinegative. Let's say you have got S4O6 dinegative. Okay. Let's say you have got Fe2O3. Let's say you have got Fe3O4. Let's say you have got Fe 0.930. Let's say you have got for example, FeCN6 4 negative, right? Lot of examples you can take. Lot of examples. Let's say you have got C3O2. Let's say you have got Br3O8. These are different examples which I've taken. And I'm selecting certain elements here. And I want you guys to calculate the oxidation states of these elements. Okay? I want you guys to calculate the oxidation states of these elements. How exactly you're going to do it? Understand. First of all, I have to calculate the oxidation state of manganese. Let the oxidation state of manganese be X. Plus, oxygen normally shows -2. There are 4 oxygen atoms. Net charge on the compound is -1. X value will be +7. The oxidation state of manganese here is +7. Right? Talk about this one. Chromium. Let its oxidation state be X. But here we have got 2 chromium, so it's going to be 2X. Oxygen shows -2. 7 oxygen atoms. Net charge -2. So X value after solving comes out to be +6. Right? Let's say you have got NH4 positive, nitrogen. X. Hydrogen is going to show +1. 4 hydrogen atoms. Net charge +1. X value would be -3. Let's say it's X, so it's going to be 3X. Oxygen shows -2. There are 2 oxygen atoms. Net charge 0, so it's going to be +4/3. Okay. Similarly, Br3O8, it's going to be +16/3. Right? When you calculate it. Fe2O3, it's going to be +3. S4O6 dinegative, it's going to be +2.5. Right? This is going to be +12 divided by 3. Sorry, +8/3. It's going to be +8/3. Oxidation state of this particular iron here. How exactly you are going to calculate? See, let the oxidation state of iron be X. How many do you have? 0.93. This oxygen is in -2 oxidation state. Net charge is 0. So X value would be equal to divided by 0.93, which comes out to be +200 divided by 93. This is the oxidation state of iron here. Okay. Now guys, one thing. Wherever you saw, okay, one more example. Let's say you have got this. NH4NO2. NH4NO2. I want you to calculate oxidation state of this nitrogen as well as this nitrogen separately. Let me tell you, this is a special compound. And in this special compound, it exists basically as NH4 positive dot NO2 negative. It exists as NH4 positive dot NO2 negative. Now, if it exists as NH4 positive NO2 negative, talk about this particular nitrogen. Let its oxidation state be X. Hydrogen shows +1. How many hydrogen? 4. Net charge here is +1. So when you solve, X value would be -3. So this nitrogen is a -3 oxidation state. Similarly, for this nitrogen, consider this as separate entity, and you will consider it as, after calculating, you'll get it as +3. Right? Okay. Am I clear with this? Now, this is the general method of basically calculating your oxidation states. One more thing. See guys, Here oxidation state came out to be fractional. Here also oxidation state came out to be fractional. Here also oxidation state came out to be fractional. Here also oxidation state fractional, right? Whenever with the help of this particular process, you get a fractional oxidation state. Remember that oxidation state is nothing but that is the average oxidation state of an element. So right here we are talking about average oxidation state of an element. I'll show you in some time how do we do its calculation. So this is the average oxidation state of an element. This is the average oxidation state of an element, right? Whenever oxidation state comes out to be zero by means of general formula, by means of general methodology. Remember that oxidation state is not the normal oxidation state. That is basically the fractional oxidation state of an element. And how do we calculate that fractional oxidation state? I'll let you know that in some time. Okay? Guys, one more important thing, right? One more important thing. This is the statement which has been asked in AIMS as well. What is that? Remember the maximum oxidation state. The maximum oxidation state of an element. The maximum oxidation state of an element can never be, the maximum oxidation state of an element can never be greater than +7. Except one example you have to remember. There are technically 3-4 examples, but one I would want you to remember particularly. Except osmium in osmium tetroxide, where it is +8. Okay, oxidation state of an element, it can never be greater than +7. You have to remember osmium in osmium tetroxide shows +8 oxidation state. That is the only exception here. Okay, that is the only exception here. Now, if this is clear, then tell me one thing. If I write CrO5, chromium pentoxide, if I write CrO5, can you tell me the oxidation state of this chromium here? I'm just asking you. What do you think? Can you tell me the oxidation state of chromium here? Quick. See, if you generally think the kind of process which I showed you, how do we do the calculation of oxidation state? If you do that process, I'll assume its oxidation state is X. Oxygen shows -2. There are 5 oxygen atoms, net charge is 0. So the value of X should be +10. But is +10 possible? Maximum oxidation state of an element can never be greater than +7. But here it's showing +10, but +10 is not possible. For example, I've got CrO6. If you do the normal process, so X, this is -2, 6, net is 0. So X is equal to +12. +12 is even not possible, right? It is not possible. So what do we do in these cases? See, we know these are not the correct oxidation states. Well, to get the correct oxidation states, what do we need? We need the actual structure of this molecule. We need the actual structure of this molecule, right? We need the actual structures of these molecules. Now, there are some very, very, very important structures which I would request, which I would want all of you to remember. Some very important structures from which questions are frequently asked. Out of which, the first structure is nothing but, the first structure is your CrO5, chromium pentoxide. Okay. Normally, it is said that it has got a butterfly-like structure, which is technically wrong, but we say that. Butterfly structure. In JEE examination long back, a question was asked, what is the color of CrO5? Remember, it's deep blue in color. Remember, it's deep blue in color. Now, how it looks like? See, this is chromium. This is double bond O. Oxygen, oxygen single bond. Oxygen, oxygen single bond. This is the structure of your CrO5. If this is the structure of CrO5, from this structure, you should know the actual oxidation state of chromium now. See guys, look at this particular bond between oxygen and chromium. Which one is more electronegative? I would say oxygen. So this bond pair will be shifted towards oxygen, so -1 and +1. Due to this bond, -1, +1. Due to this particular bond, -1, +1. Due to this bond, -1, +1. Due to the double bond, -2, +2. Now, check the total charge on chromium. +2, +3, +4, +5, +6. So, the actual oxidation state of chromium in CrO5 is +6. A question will be asked, how many oxygen atoms are there with -1 oxidation state? This oxygen is a -1, this is a -1, this is a -1, this is a -1. So there are 4 oxygen atoms present in -1 oxidation state. Question will be asked, how many peroxide linkages would be there? Peroxide means oxygen single bond oxygen. Do you see this is a peroxide linkage? Oxygen single bond, oxygen single bond. So 2 peroxide linkages are there. These are the different questions which can be asked from your CrO5, right? Now similarly, there are many structures like these which you are going to remember. For example, you have got CrO6. This is the question asked in your NEET 22 as well. CrO6. What is the oxidation state of chromium in CrO6? Well, you should know it. First of all, if I talk about the CrO6 structure, this is chromium, oxygen, oxygen single bond, oxygen, oxygen single bond, oxygen, oxygen single bond. This is your CrO6 structure. If you look at this structure and calculate the oxidation state of chromium, it will come out to be +6, right? If I ask you how many peroxide linkages are there, 1, 2, 3. There are 3 peroxide linkages. If there are 3 peroxide linkages, how many oxygen atoms are there with -1 oxidation state? Do one thing, peroxide linkage multiplied by 2. So 3 multiplied by 2 is 6. Nothing more than that. Nothing more than that. So this was your structure number 2. When you talk about your structure number 3, that is your Carr's acid. Carr's acid, which is H2SO5. Carr's acid, H2SO5. So first of all, you need to know the structure of your Carr's acid as well. This is S, double bond O, oxygen attached with hydrogen. This is oxygen, oxygen, hydrogen. This is the structure of your H2SO5. Now, what all things we have to remember about H2SO5? Have a look. S double bond O. Which element is more electronegative? Oxygen. So it will show -2. This will show +2. Due to this double bond, -2, +2. Due to this single bond, -1, +1. Due to this single bond, -1, +1. What is the total charge on the sulfur here? +2, +4, +5, +6. So actual oxidation state of sulfur in Carr's acid is +6. Right? Now similarly, guys, if I ask you how many peroxide linkages do you see? Peroxide linkage means oxygen single bond oxygen. It's a peroxide linkage. So there is 1 peroxide linkage. How many oxygen atoms are there with -1 oxidation state? Peroxide linkage multiplied by 2. Right? This was the third structure from which question comes. Now, this was your Carr's acid. The fourth is your, I hope you have heard about oleum. H2S2O7. Right? How this H2S2O7 looks like. Understand properly. This is S, oxygen, sulfur, double bond O, oxygen attached with hydrogen. This is double bond O, oxygen attached with hydrogen. This is the structure of your H2S2O7. Okay. Now guys, try to understand properly. This is S double bond O. Which one is more electronegative? Oxygen. So -2, +2. This double bond, -2, +2. This single bond, -1, +1. This single bond, -1, +1. So total charge on sulfur is +2, +3, +4, +6. So this sulfur is in +6 oxidation state. Similarly, this sulfur is in +6 oxidation state. Right? Now guys, there are 2 sulfur atoms. So if I want to calculate average oxidation state of sulfur, see the first sulfur has got +6, second sulfur has got +6. There are 2 sulfur atoms. So average is +6. Average is +6. How do you remember these structures? With the help of practice only. There is no shortcut to them. There is no shortcut to them. Somebody will say there are shortcuts. No. You have to remember them. Okay. There are few more structures. This was your oleum. Similarly, you have got your fifth one, that is your Marshall's acid. That is your Marshall's acid. Marshall's acid formula, I don't know whether you know it or not. H2S2O8, and this is SOOS, double bond O, oxygen with hydrogen, double bond, oxygen with hydrogen. This is the structure of your H2S2O8. Okay. Now guys, when you calculate the oxidation states, oxidation state of this sulfur would be +6, even this sulfur would be +6. And when you calculate average oxidation state of sulfur, first one is showing +6, second is also +6, total 2 sulfur atoms, average is +6. This is your Marshall's acid. Sixth one is your important one, Na2S4O6. 2 times questions have been asked from this compound in your JEE examination. Na2S4O6. So first of all, you should remember its structure. It is 4 sulfur atoms with a single bond, double bond O, double bond O, double bond, double bond, oxygen with sodium, and this is oxygen with sodium. Now you have to remember all this stuff. If you talk about the oxidation state of this sulfur, plus 2 from this oxygen, plus 2 from this oxygen, plus 1, that's it. So plus 5. This sulfur, 0 oxidation state. This sulfur, 0 oxidation state. This sulfur, plus 5 oxidation state. If I talk about average oxidation state of sulfur, the first one is plus 5, second is 0, third is 0, fourth is plus 5, total 4 sulfur atoms. So it is plus 2.5. It is average. Right? It is average. Remember this particular point as well. Similarly, seventh structure is your K3CrO8. I hope you have heard about this. K3CrO8. Its structure, from its structure, the question is again asked. So its structure is like this: Cr, oxygen, oxygen, single bond, oxygen, 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 potassium attached, potassium and potassium. So this is your K3CrO8. And in this K3CrO8, oxidation state of chromium would be, there are 5 bonds with oxygen, so plus 5 directly. Okay. How many peroxide linkages did they ask you? Peroxide means this is one peroxide, second, third, fourth. So 4 peroxide linkages. So how many oxygen atoms with -1 oxidation state? 4 2s are 8. So till now, some 7 structures we made. Okay. 8th structure. 8th structure is going to be your C3O2. Your textbook example, this is C3O2. This is how your C3O2 looks like. 9th example is your Br3O8. This is your Br3O8. 10th structure is your bleaching powder, CaOCl2. CaOCl2. It's an ionic compound though. I'm just making the structure so that you can remember it. The next structure is going to be your BaSCN whole twice. The next structure is going to be your H3PO2. Next is going to be H3PO3. Next is going to be your H3PO4. Next is going to be your H3PO5. So remember their structures as well. Draw P double bond O everywhere first. This is oxygen attached with hydrogen. Hydrogen and hydrogen. These are the structures, guys, which you have to remember. Okay? These are the structures which you have to remember. For example, if you look at your C3O2, look at the C3O2. Just look at it. There's a double bond between carbon and oxygen. Okay? Which one is more electronegative? Oxygen. So this will be -2, this will be +2. There is a double bond here, -2, +2. On towards this carbon, this side also carbon, this side also carbon, nothing. So if I talk about the average oxidation state of carbon, the first carbon is having +2, second is having 0, third is having +2. 3 carbon atoms in total, so it's going to be +4/3. Right? +4/3. This is the average oxidation state of carbon. Similarly, your bromine. This bromine has got 3 oxygen atoms with double bond, so +6. 2 oxygen atoms means +4. This is +6. So if you want to calculate average oxidation state of bromine, This would be plus 6 plus 4 plus 6 divided by 3. So plus 16 by 3 it's going to be. Plus 16 by 3 it's going to be. See, this is OCl, oxygen more electronegative, minus 1 plus 1. Minus 1 plus 1. Minus 1 plus 1. One chlorine plus 1, another in minus 1. So average oxidation state of chlorine is going to be 1 chlorine is plus 1, another is minus 1. Total 2 chlorine atoms. Average oxidation state of chlorine here is going to be 0. Here is going to be 0. Okay. Similarly, BaSCN whole twice. BaSCN whole twice. This is carbon triple bond nitrogen. So minus 3 plus 3. Carbon triple bond nitrogen minus 3 plus 3. Carbon and sulfur. Sulfur more electronegative, minus 1 plus 1. Barium sulfur minus 1 plus 1. Barium sulfur minus 1 plus 1. Carbon sulfur minus 1 plus 1. Now get the oxidation state of all these elements. Nitrogen will be minus 3. Carbon will be plus 3 plus 1 plus 4. Sulfur is going to be minus 2. Barium is going to be plus 2. This sulfur minus 2. This carbon plus 3 plus 1 plus 4. This is minus 3. I hope all this stuff is understood, right? Similarly, this phosphorus here will be in plus 1 oxidation state. This would be in plus 3 oxidation state. This would be in plus 5 oxidation state. Even this is going to be in plus 5 oxidation. So these are the different structures, my dear students, which you have to remember on priority. If I am clear, let me know once in the chats. And I want you guys to take the screenshot of this particular slide as well, because these structures are very, very, very important. Is it all clear? How many tests you need to write? Keep on writing tests on every Sundays first, right? And in the last month, write almost like 30, 40 mock tests. That is sufficient. Redox will take further 2 hours. In 2 more hours, it will be done. Sir, will you be doing thermochemistry? We'll see till what topics will be like. Let's see. Let's see. I don't know. Let's see how many chapters, how many topics we can cover in 12 hours. We'll do that. Don't worry. Just give me a second. Mhm. You can ask me any questions till then, like whatever questions you have related to the preparation. Do you have any questions or not? Or you are done with the questions? Next chapter would be atomic structure. Next chapter would be atomic structure. Next is going to be atomic structure, yes. All right. Exactly. The paper in the JEE paper was easy. Yesterday's both the shifts were easy, very easy. I'll give you the break at 5, not now. Even I've not had my lunch yet. We'll have it at 5. Okay? We'll have it at 5. Is that okay? Yes, yesterday's JEE shifts were both the shifts were very easy. Both the shifts were easy, yes. Okay, let's move on. Let's move on now. I hope you're familiar with the term oxidation state now. Okay, now let's exactly see what is meant by the term oxidation and what is meant by the term reduction. What is meant by the term reduction? See, this is something which you had been, I think you have been seeing from your class 10th. From your class 10th. Okay, have a look. When it comes to your oxidation, oxidation first of all involves what? It involves loss of electrons. Oxidation, it involves loss of electrons, number one. Oxidation involves a removal of hydrogen. Any reaction which involves a removal of hydrogen, that's also what you call as oxidation. I'll give the example in some time. Any reaction which involves addition of oxygen. Any reaction which involves addition of oxygen. That's also what you call as oxidation. And any reaction that involves addition of more electronegative element. That's also what you call as oxidation. So these are few ways by means of which you can define the term oxidation. Loss of electrons, removal of hydrogen, addition of oxygen, addition of more electronegative element. In the similar way, you can define reduction as well. Gain of electrons, addition of hydrogen, removal of oxygen, and removal of more electronegative element. Let me give you the examples so that you'll understand. See guys, look at this particular reaction. In this reaction, what is happening? Is the loss of electrons taking place or gain? I would say 2 electrons are lost by magnesium. The loss of electrons is happening, right? Loss of electrons is happening, oxidation. In this particular reaction, what is happening? I'll say hydrogen is removed from water. So removal of hydrogen is taking place. It is again the example of oxidation. Look at this one. Calcium plus O2 gives CaO, calcium oxide. In this reaction, addition of oxygen is taking place. This is also oxidation. In this reaction, addition of more electronegative element is happening. That means it is also the example of oxidation. It is also the example of oxidation. So, in oxidation, loss of electrons, removal of hydrogen, addition of oxygen, or addition of more electronegative element takes place. Now, this is something which you are not going to remember. See what is common in all the reactions. That's something which we shall be discussing. What is common? Have a look. Have a look, guys. If I ask you what is the oxidation state of magnesium here, you'll say 0. What is the oxidation state of magnesium here? It is +2. Is the oxidation state of magnesium increasing or decreasing? 0 to +2. Increase in the oxidation state. The oxidation state of magnesium is increasing. Look at this water. Oxygen. Oxygen is at -2. This oxygen is 0. Oxidation state of oxygen is also increasing. Simple. Calcium, its oxidation state is 0. Here it is +2. 0 to +2, again increase in the oxidation state. Right? Carbon, here 0. Here it is +4. 0 to +4, again increase in the oxidation state. First of all these reactions are the examples of oxidation reactions. All these reactions are the examples of what? Oxidation reactions. And everywhere, if you notice one thing, increase in the oxidation state is happening. So from now onwards, I just want you guys to remember one thing. Oxidation involves increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So whenever in any reaction, whenever you see oxidation state of any element increasing, in a reaction when you see oxidation state of an element increasing, understand that element will be undergoing oxidation. And if the element undergoes oxidation, that will be losing electrons. That would be losing electrons. Similarly, reverse to it, I would say decrease in the oxidation state is what I'll be calling as. Decrease in the oxidation state is what I'll be calling as. What I'll be calling as reduction. Decrease in the oxidation state is what you'll be calling as reduction. Okay? Am I clear with this? If these two things are clear, then there comes two more things. There's something which I told you. In oxidation, oxidation state of an element increases. In reduction, oxidation state of an element decreases. Now, my dear students, what are your oxidizing agents and reducing agents? That's again important. See, first of all, I'll write the definition, then I'll make you understand. If you talk about the oxidizing agent, or what you call as oxidant, oxidizing agent or oxidant. What is oxidizing agent? It is that species. It is that species. That species which oxidizes others. That species which oxidizes others, but itself undergoes reduction. That species which oxidizes others. That species which can oxidize others, but itself undergoes reduction. That oxidizes others, itself undergoes reduction. What is meant by that, you'll understand in some time. But before that, let me take down the definition of your reducing agent as well. Reducing agent or reductant. Reducing agent or reductant. See, reducing agent is the one. It is that species. That species which reduces others. Which reduces others, but itself undergoes oxidation. That species which reduces others, but itself undergoes oxidation, reducing agent. That species which oxidizes others, itself undergoes reduction, oxidizing agent. Now understand what it means. See guys, for example, I've taken a reaction over here. What is the oxidation state of magnesium? 0. Oxygen 0. Magnesium plus 2. This oxygen is minus 2. What is happening to the oxidation state of magnesium? 0 to plus 2, increase. Increase in the oxidation state is what you call as oxidation. Increase in the oxidation state is what you call as oxidation. And the one that undergoes oxidation, that loses electrons. That loses electrons. At the same time, the one that undergoes oxidation is called as the reducing agent. The one that undergoes oxidation is what you call as the reducing agent. Similarly, 0 to minus 2, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. Decrease in the oxidation state is what you call as reduction. Reduction involves gain of electrons. Reduction involves gain of electrons. And that species which undergoes reduction is something which you will be calling as the oxidizing agent. Okay? So basically, reducing agent is the one which reduces others, itself undergoes oxidation. Oxidizing agent is the one that oxidizes others, but itself undergoes a reduction. As simple as that. Okay? For example, this is the reaction, and you have to identify which one is your oxidizing agent and which one is your reducing agent. How do I do it exactly? Iron is in +2 oxidation state. Manganese is in +7 oxidation state. This iron is in +3 oxidation state. This manganese is in +2 oxidation state. And we have seen how do we do the calculation of oxidation states. Now, my dear students, try to understand one thing. +2 to +3. increase. Plus 7 to plus 2, decrease. Increase in the oxidation state is what you call as oxidation. So I would say this FeO is undergoing oxidation. The one that undergoes oxidation is your reducing agent. MnO4 negative, oxidation state decreasing. Decrease is what we call as a reduction. And the one that undergoes reduction is going to be your oxidizing agent. Okay, is going to be your oxidizing agent. I hope this is clear. Similarly, let me take one more example so that it will be like properly clear. Zinc, its oxidation state here is 0. Copper here is in plus 2 oxidation state. Zinc is in plus 2 oxidation state. Copper is in 0 oxidation state. Now what is happening? 0 to plus 2, increase in the oxidation state. 0 to plus 2, increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So I would say this zinc is undergoing oxidation. It would be losing electrons. And the one that undergoes oxidation is your reducing agent. Plus 2 to 0, decrease. Decrease means reduction. So this copper di positive is undergoing reduction. The one that undergoes reduction is going to be your oxidizing agent. Am I clear with this? Am I clear with this, guys? Is it clear till here? Is it clear till here? Spectator ion is the one whose oxidation state does not change, basically. I'll show you when I teach you balancing. I'll show it there. So this was all about your oxidizing agent and reducing agent and how do we identify it. Now comes one of the most important part of this chapter. What is that? That's equivalent mass. Okay, that is equivalent mass. That is equivalent mass. Or before doing the equivalent mass. Before doing the equivalent mass. If I ask you some questions related to oxidizing and reducing agents, let me see if you can solve them or not. For example, I'm writing certain compounds. H3PO4 is the first compound which I'm writing. HCl, okay. Your KMNO4, H2O2, K2Cr2O7. You have to tell me the nature of these compounds. You have to tell me the nature of these compounds, whether they are oxidizing agents, reducing agents, or they can behave like both, oxidizing as well as reducing. See guys, first thing, you need to highlight the central atom here. I've highlighted the atoms. Okay. What is the oxidation state of phosphorus in the first compound? In this compound, oxidation state of phosphorus is plus 5, chlorine is a -1, magnesium is in plus 7, oxygen is a -1, and your chromium here is in plus 6. These are their respective oxidation states. Yes. Now, all these phosphorus, chlorine, manganese, oxygen, right? Leaving chromium aside, all these are your what? All these are your p block elements. All these are your p block elements. And I have told you in case of p block elements, oxidation state, it varies from group number -18 to group number -10. Group number -18 to group number -10. So first of all, here you have got phosphorus. You have got phosphorus. If I talk about phosphorus, what about phosphorus? The range of oxidation state for phosphorus is group 15. So 15 minus 18 is -3. -3. 15 minus 10 is +5. Phosphorus can go from -3 to +5. Phosphorus can go from -3 to +5. In this particular compound, phosphorus is already in +5. It is already in +5. So phosphorus is already in maximum oxidation state. In this compound, phosphorus is already in maximum oxidation state. So if phosphorus is already in maximum oxidation state, it cannot further increase its oxidation state. It cannot further increase its oxidation state. If it cannot further increase its oxidation state, it cannot undergo oxidation. The one that cannot undergo oxidation, the one that cannot undergo oxidation, that cannot behave like the reducing agent. So it is only going to behave like the oxidizing agent. Did you understand? Chlorine. Talk about chlorine. Group 17. 17 minus 18 is minus 1. 17 minus 10 is plus 7. And here chlorine is in minus 1. The range shown by chlorine is this to this. And chlorine is already in minus 1. Chlorine is already in minimum oxidation state. If chlorine already is in minimum oxidation state, it cannot further decrease its oxidation state. It cannot further undergo reduction. It cannot behave like an oxidizing agent. So that means it will behave like a reducing agent. You got it? Manganese. Your manganese, your D block element. The maximum oxidation state shown by manganese is, I told you already, that's plus 7. Plus 7. And manganese already here is in maximum oxidation state, plus 7. Right? So it cannot increase, it cannot undergo oxidation, it cannot behave like a reducing agent. That means it can behave only like oxidizing agent. H2O2. Oxygen here is in minus 1. Oxygen, group 16. Group 16. Group 16. 16 minus 18 is minus 2. 16 minus 10 is plus 6. Oxygen here is in minus 1 oxidation state. The range shown by oxygen is between minus 2 to plus 6. And oxygen is in minus 1. So it can decrease also, it can increase also. It can decrease also, it can increase also. So this compound can show both oxidizing agent as well as a reducing agent. Right? Chromium. Chromium's maximum oxidation state is already plus 6. So it is going to be the oxidizing agent. Is this particular rule clear? Did you understand how do we check whether the substance is going to behave like oxidizing agent, reducing agent, or both? Is it clear? Can you tell me about this one? HNO2. What kind of nature it's going to show? Quickly, tell me in the chats. I'll sit for a moment then. Tell me in the chats, quickly. I would want answers from everyone. HNO2. Quickly. Guys, quickly. In case of HNO2, what is the oxidation state of nitrogen? In case of your HNO2, what is the oxidation state of your nitrogen? It's going to be plus 3. What is the range of oxidation state shown by nitrogen? It's group 15. Group 15 goes from minus 3 to plus 5. Minus 3 to plus 5. So, its oxidation state is plus 3. So, it can decrease also, it can increase also. So, it has got the dual nature. It can behave like oxidizing agent as well as a reducing agent. Right? I hope this is clear. Now we are going to enter into one more important phase of this particular chapter. What is that? That is your equivalent mass. That is your equivalent mass. How do we exactly define the term equivalent mass? Number one. Okay. What kind of questions can be asked out of this? Let's try to understand all of this in detail. See guys, if I try to define the term equivalent mass, I would say it is defined as that mass of substance in grams, which can combine or displace. That mass of the substance in grams which can combine or displace either 1 gram of hydrogen, or 8 grams of oxygen, or 35.5 grams of chlorine, or 108 grams of silver, or 80 grams of bromine, etc. Now see what it means. See what all things we can understand from this. That mass of the substance which can combine, or displace either 1 gram hydrogen, or 8 grams of oxygen, or 35.5 grams of chlorine, or 108 grams of silver, etc. See, for example, my dear students, let's say I'm writing a reaction here. The reaction is pretty much simple, like N2 plus 3 times H2 gives 2 times NH3. It's a very common reaction, you know it. It's a very common reaction. If you look in this particular reaction, nitrogen is combining with what? Nitrogen is combining with hydrogen. First of all, I'll just use stoichiometry. Tell me one thing. What is the molar mass of H2? I would say molar mass of H2 is 2 grams. Molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. Mass of 1 mole of H2 is 2 grams. So mass of 3 moles of H2 would be 6 grams. So I would write 6 grams of hydrogen. What is the molar mass of N2? 28 grams. That means mass of 1 mole of N2 is 28 grams. So can I say stoichiometry is telling us one thing? 6 grams of hydrogen combines with 28 grams of nitrogen. If I use the unitary method, I can say 1 gram of hydrogen combines with 28 by 6. That means 14 divided by 3 grams of nitrogen. Right? 1 gram of hydrogen combines with 14 by 3 grams of nitrogen. My dear students, look at the definition. That mass of the substance which can combine or displace 1 gram of hydrogen. That mass of substance which can combine with 1 gram of hydrogen is what you call as the equivalent mass. Can I say this is the mass of nitrogen? This is the mass of nitrogen which has combined with 1 gram of hydrogen. This is the mass of nitrogen that has combined with 1 gram of hydrogen. And that mass of substance which combines with 1 gram hydrogen is what I call as equivalent mass. So equivalent mass of nitrogen here is simply 14 by 3 grams. That's all. Am I clear with this? Equivalent mass you can calculate with respect to hydrogen like I did right now. You can calculate it with respect to oxygen as well. But when you are calculating with respect to oxygen, you have to check for 8 grams of oxygen. Similarly, chlorine, silver, bromine. Let me take few more examples. For example, let's say you have got let's say I'm writing a reaction, MgO. Okay? This is for example half. This for example half. Try to understand what I say. Tell me one thing. What is the molar mass of O2? Molar mass of O2 is 32 grams. That means mass of 1 mole of O2 is 32 grams. But I have half mole. Half mole means 16 grams. So I can write 16 grams of oxygen. 16 grams of oxygen combines with, what is the mass of 1 mole magnesium? 24 grams. So stoichiometry is telling us that 16 grams of oxygen combines with 24 grams of magnesium. Therefore, 1 gram oxygen combines with 24 by 16 grams of magnesium. As per the definition, I would say 8 grams of oxygen would combine with 12 grams of magnesium. If you look carefully, what is this particular term? I would say this is the mass of magnesium. This is the mass of magnesium that has combined with 8 grams of oxygen. This is the mass of magnesium that has combined with 8 grams of oxygen. And that mass of substance which combines either with 1 gram hydrogen or 8 grams of oxygen, what do we call that as? Equivalent mass. So this is something which I'll be calling as equivalent mass of magnesium. I hope I'm clear with this. Now guys, all this you are not supposed to remember, okay, in very much detail. The points that are to be remembered, I'm going to tell you them now. What are those points? See, in order to calculate equivalent mass of any substance, we are going to use a formula, a result. What is the formula? What is the result? Equivalent mass of any substance is always equal to molar mass of the substance divided by n factor, or you call it as the valency factor. Equivalent mass of the substance is always equal to molar mass of the substance divided by what? Divided by n factor of substance, or we call it as the valency factor of the substance. Right? Molar mass of any substance you know. Molar mass of substances you already know. You just need to know how to calculate n factor of substances. Just divide them up and you'll be getting what? You'll be getting the equivalent mass of a substance. Few cases and it'll be all clear. For example, the first case, n factor of an element. N factor of an element. N factor of an element is nothing but valency of an element. N factor of an element is nothing but valency of an element. For example, you take any element. Let's say we have got nitrogen. Let's say we have got oxygen. Let's say we have got sodium. Let's say we have got magnesium. Okay. What is the valency of nitrogen? 3. Valency of oxygen? 2. Valency of sodium? 1. Valency of magnesium? 2. Valency of an element is what you call as their n factors. So I would say this is the n factor of nitrogen, n factor of oxygen, n factor of sodium, n factor of magnesium. And if you get the n factors, you can easily calculate their equivalent masses. So equivalent mass of nitrogen is nothing but molar mass of nitrogen divided by its n factor. Right? Equivalent mass of oxygen would be molar mass of oxygen divided by its n factor. Equivalent mass of sodium would be molar mass of sodium divided by its n factor. Equivalent mass of magnesium would be molar mass of magnesium divided by its n factor. Okay. So first case of n factor. N factor of an element is nothing but it is the valency of an element. Number two. N factor of an ion. N factor of an ion is nothing but the charge present on an ion. N factor of an ion is nothing but the charge present on an ion. Let's say you have got Na positive. Let's say you have got Cl negative. You have got SO4 dinegative. You have got PO4 trinegative. These are different ions which we have. And what is the charge present on the sodium? It's +1. Charge present on chlorine, -1. Sulfate, -2. Phosphate, -3. Take the magnitude of charge. This is magnitude, okay? N factor of an ion is equal to magnitude of charge present on an ion. Now, magnitude of the charge. If you look at the first case, Na positive. The charge here is +1. If I talk about only the magnitude here is 1. -1, its magnitude is 1. -2, its magnitude is 2. -3, its magnitude is 3. And magnitude of charge on an ion defines its n factor. So n factor, you got basically These are n factor of all these ions. Perfect. Moving on to the third case. Moving on to the third case. What is that? That is n factor of a salt. N factor of a salt. N factor of a salt is nothing but, it is the LCM of, it is the LCM of charge on cation, comma, the charge on anion. LCM of charge on cation and charge on anion. Okay. Now, my dear students, if you look carefully, take any salt, NaCl, right? One of the very common salts. For example, you have got BaCl2. Let's say you have got AlCl3. Let's say you have got Al2SO4 whole thrice. These are different salts which we have. Now, the charge on cation is +1, anion is -1. +2, -1. Crisscross, +3, -1. Crisscross, +3, -2. Now, what is the LCM of 1 and 1? LCM of 1 and 1 is 1. What is the LCM of 2 and 1? That's 2. LCM of 3 and 1 is 3. LCM of 3 and 2 is 6. LCM of charge of cation and anion, that gives me the n factors. Yes, you can watch it for boards as well. I hope this is super clear to everyone. Okay. N factor of a salt is nothing but LCM of charge on cation and anion. That's it. Okay. Now the fourth case here. The fourth case, that is important. What is that? That is n factor of an acid. N factor of an acid. Let me tell you, n factor of acid is nothing but, it is basicity of an acid. N factor of an acid is nothing but basicity of an acid. Okay. And basicity, I'm going to classify in many ways. Number one, number of H positives an acid donates. Number of H positives an acid donates. Number two, number of OH negatives an acid accepts. Okay. Or you can say number of lone pairs an acid accepts. These are the three ways by means of which I can define the basicity. And whatever is the basicity, that's going to be your n factor. Now we will try to understand certain important things which I'm going to tell you. Some important things. For example, if I take some common acids, HCl, H2SO4, H3PO4, HNO3. Just tell me one thing. When you introduce them in water, how many H positives this acid is going to donate? It will donate 1 H positive. This will donate 2 H positives. This will donate 3 H positives. This will donate 1 H positive. The number of H positives an acid donates. Sir, I'm following your game of NEET. Just follow that. That's enough. Okay. Do not spam, please. See, the number of H positives an acid donates, that defines its basicity, and whatever is the basicity of the acid, that's going to be the n factor. So n factor of HCl here is 1. N factor of H2SO4 here is 2. Here it's 3. Here it's 1. So these are the respective n factors. And if you got the n factors, you can easily calculate their equivalent weights. How? Their molar mass divided by their n factor. Molar mass divided by their n factor. Okay? Now guys, one more thing. One more thing. Remember, an acid donates only that H positive. An acid donates only that H positive, which is attached to more electronegative element like fluorine, oxygen, or nitrogen. More electronegative element like fluorine, oxygen, nitrogen. An acid donates only that H positive, which is attached to more electronegative element like fluorine, oxygen, nitrogen. For example, let's say you have got H3PO2. You have got H3PO3. You have got H3PO4. Let's say you have got H3PO5. If you make their structures, This is P double bond O. Everywhere I'm introducing P double bond O first. Everywhere I'm introducing P double bond O. This is oxygen attached with hydrogen. And this is hydrogen and hydrogen. Oxygen with hydrogen. Oxygen with hydrogen. This is hydrogen. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen. 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 Now, first of all, normally if you see, in this particular compound, there are total 3 hydrogen atoms. There are 3 hydrogen atoms. Out of these 3 hydrogens, there is only 1 hydrogen which is attached to more electronegative element like oxygen. Here you have got 2 hydrogens attached to more electronegative. Here you have got 3 hydrogens attached to more electronegative. Similarly, 3 hydrogens attached to more electronegative. And we know an acid donates only that H positive. An acid donates only that H positive which is attached to more electronegative element. So here, I would say this acid will donate only 1 H positive. This acid will donate 2 H positives. This acid will donate all the 3 H positives. This acid will donate all the 3 H positives. So these are the N factors of these acids. And if you got these N factors, you can easily calculate their equivalent weights. How? Their molar mass divided by their N factors. I hope I'm clear with this. Now one more thing. Let me write a reaction. H2SO4 plus 2 times NaOH. It gives Na2SO4 plus 2 times water. This is one of the reaction. Second reaction is, let's say H2SO4 plus NaOH gives NaHSO4, and with this you have got water. So 2 reactions I have. Okay. I want to calculate N factor of H2SO4 here and N factor of H2SO4 here. Okay. How do I do it? Try to understand. My dear students, you must be knowing, if one H positive interacts with one OH negative, what do we get? We get 1 water molecule. Right? In the similar way, if 2 H positives interact with 2 OH negatives, what do we get? We get 2 water molecules. In the first case, 2 water molecules are being formed. How 2 water molecules would have got formed? When this would have given 2 H positives, this would have given 2 OH negatives, right? And eventually 2 water molecules would have got formed, right? Similarly here, 1 water molecule is being formed. 1 water molecule will be only formed if this gives 1 H positive, this gives 1 OH negative, and they would have interacted and formed 1 water molecule. The number of H positives that an acid donates, that defines its N factor. Here, 2 H positives, here 1 H positive. So in the first case, N factor of H2SO4 is 2. In the second case, N factor of H2SO4 is 1. Right? So equivalent mass of H2SO4 in the first reaction would be M divided by 2. Here it's going to be M divided by 1. Which means equivalent mass is a variable quantity. It's not a fixed quantity. It's a variable quantity. It's not a fixed quantity. Am I clear? Am I clear with this? Is it clear, guys? All right, one more thing. One more thing which I would want you guys to remember. That's also a special case. Have you heard about boric acid? H3BO3. Or sometimes, just to confuse you, they write it like this. BOH whole thrice. It's a boric acid. It's boric acid, okay? Normally, if I ask you what is the N factor of boric acid, you will say it has got 3 hydrogens. It will leave 3 H positives. So its N factor should be 3. That should be your normal response. But let me tell you, when this boric acid is introduced in water, it gets converted into BOH4 negative plus H positive. This boric acid, it is not the protic acid. It is not the protic acid. It's a weak Lewis acid. Remember, it is a weak. It's a weak Lewis acid. Now, what about its N factor? See, if you look carefully, here it has got 3 OH. Now in water, it got converted into this species where it has 4 OH. So how many OH negatives it has accepted? This boric acid. This boric acid, how many OH negatives it has accepted? I would simply say it has accepted 1 OH negative. And the number of OH negatives an acid accepts, number of OH negatives an acid accepts, that also defines its basicity. And whatever is the basicity, that's going to be the N factor. So remember, N factor of boric acid here in this particular case is going to be 1. Am I clear? Am I clear, guys? Am I clear to everyone? Okay. Now, before continuing the rest of the things, let's take a break, and it's going to be a lunch break for me. And for a lot of you, it is lunch break as well. So let's take the break till it's 4:55. What time you guys will be back? Tell me. Tell me what time you guys are going to be back. 5:30 is a good time, I think. Yeah. But I would want every one of you to be back, okay? I would want every one of you to be back. I would want every one of you to be back. Hello, I'll have my dinner. I'm sorry, I'll have my lunch, not the dinner. And after that, we'll see, we'll check again. Huh? Okay. Basit, not all the hydrogens. In case of H3PO4, there are only 3 hydrogens. Okay. Wait, what are you saying? Just. They said the hydrogen which is attached to oxygen in acid H3PO4 are acidic. Of course, in H3PO4, there are 3 hydrogens. And all the 3 hydrogens are attached to 3 oxygen atoms. So all the 3 would be acidic only. All the 3 would be acidic only. Correct only. That's what you wrote here also. Where are the structures? That's what you wrote here also. In H3PO4, all the 3 hydrogens, they're acidic only. Okay? Chalo. I'll see you guys after the break, huh? But everyone, be there on time. Guys, can you all hear me? Am I audible again? Am I audible? Welcome back, welcome back, welcome back. So what was the last thing that we discussed? What was the last thing that we discussed? Yes, I'm done with my lunch. Tell me, what was the last thing that we discussed? Yes, game of NEET is very much enough. That's very detailed. So we discussed about the N factor of an acid, right? Got it, got it, got it. We discussed about N factor of an acid. So let's move on then. Let's get started with the N factor of a base. N factor of a base. My dear students, let me tell you N factor of a base. How do we define it? N factor of a base is defined as the acidity of the base. N factor of a base is defined as the acidity of the base. And how do we define this acidity? Number of OH negatives a base donates, or you can say number of H positives a base accepts. Number of H positives a base accepts. Okay. For example, let me take some very common bases. You all must be knowing about them. Let's say we have got NaOH, a very common base. We have got BaOH whole twice, one more base. My dear students, just tell me one thing. When you introduce these bases in water, how many OH negatives you guys are going to get? This base will furnish one OH negative, and this base will furnish two OH negatives. And number of OH negatives furnished by a base. Number of OH negatives furnished by a base. That defines its N factor. So N factor of NaOH here in this particular reaction is 1. N factor of NaOH here in this particular reaction is 2. Okay? And once you get the N factor of these bases, you can easily calculate their equivalent weights. How exactly? Molecular weight divided by N factor. Point number 1. Point number 1. Point number 2. For example, I've got a base like NH3. I've got a base like NH3. You know, nitrogen, it has got one lone pair. Okay. Now this NH3, when it's introduced in water, it gets converted into what? It gets converted into NH4 positive. Perfect. If you look at this particular reaction, NH3, it had three hydrogens attached with it. Nitrogen, I mean. Now it got converted into NH4 positive. What is happening? Can I say NH3 has gained one H positive, then it has got converted into NH4 positive, right? And the number of H positives that a base accepts, that also defines its N factor. So first of all, in this particular reaction, this NH3 has accepted one H positive from water and got converted into NH4 positive. And we know number of H positives that a base accepts, that defines its N factor. So here in this particular reaction, N factor of this particular base is 1. Okay. And people, if N factor of this base is 1, you can easily calculate its equivalent weight. How exactly? Molecular mass divided by its N factor. right? Similarly, let me take a few more examples. Let's say you've got a reaction like this. ZnOH whole twice plus 2 times HCl. Let's say it gives ZnCl2. And with this, you're getting 2 times water as well. For example, in this particular reaction, I need to calculate N factor of this particular base. Can we do that? Can we do it? It can be easily done. If you see properly, first of all, here in this reaction, 2 molecules of water are formed. Or you can say 2 moles of water are formed. I'll say how these 2 moles of water would have got formed when this base would have donated 2 OH negatives, and from this acid 2 H positives would have come, and they would have interacted and formed 2 water molecules. So can I say this particular base, it is donating 2 OH negatives? And you know, the number of OH negatives the base donates, that defines its N factor. So in this particular reaction, N factor of zinc hydroxide here is 2. As simple as that. For example, if I modify the similar reaction, if I modify the reaction like this, let's say you have got zinc hydroxide plus HCl, and for example, I'm getting ZnOHCl, and with this I'm writing water. Let's say there's one more reaction. And in this particular reaction, let's say I'm asking you to calculate N factor of this particular base. If you look carefully, in this balanced chemical equation, 1 water molecule is being formed. And I would say, in order to form 1 water molecule, this base should have given 1 OH negative. This acid should have given 1 H positive. And these 2 would have interacted and formed this 1 water molecule. Right? So this particular base, it is donating 1 OH negative. And the number of OH negatives that a base donates, that also defines its N factor. So N factor of this particular base here is 1. So this is how you calculate N factor for bases as well. I believe I'm clear with this. Okay. Now comes the most important point. What is that? That is your N factors of oxidizing agents and reducing agents. How do we calculate the N factor of oxidizing agents and reducing agents? My dear students, N factor of oxidizing or reducing agents is nothing but it is the number of moles of electrons. Number of moles of electrons. Number of moles of electrons. Lost, gained, or I would say exchanged. Number of moles of electrons lost, gained, or exchanged. By what? By 1 mole of substance. Lost, gained, or exchanged by 1 mole of substance. For example, let's say you've got a reaction like this, A plus B, a general reaction. Let's say it gives A positive plus B negative. This is your reaction. Now, if this is the reaction, for example, oxidation state of this A is 0, here it's 0, here the oxidation state is +1, here the oxidation state is -1. Okay? What is happening to the oxidation state of A? Is it increasing or decreasing? 0 to +1, increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So this A is undergoing oxidation. This A is undergoing oxidation. If A undergoes oxidation, that means it will be losing electrons. And the one that undergoes oxidation is what you call as a reducing agent. So A is your reducing agent here. Right? Talk about B, 0 to -1, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. Reduction means gain of electrons. So this B gains electrons. And the one that undergoes reduction is what you call as oxidizing agent. Is what you call as oxidizing agent. Yes? Now, my dear students, for example, I want to calculate N factor of A here. I want to calculate N factor of A. Since A is undergoing oxidation, A is losing electrons. I want to calculate N factor of A. What does that mean? That means I want to calculate number of moles of electrons lost by 1 mole of A. That means I want to calculate number of moles of electrons lost by 1 mole of A. Similarly, for example, I want to calculate N factor of B. What is B doing? B is gaining electrons. N factor of B means number of moles of electrons number of moles of electrons gained by, I would say, 1 mole of B. By 1 mole of B. Now, how do we exactly get it? How do we exactly get to know the moles of electrons lost or gained by these substances? See guys, there is a simple trick by means of which you can do that. N factor of A is equal. N factor of A is equal. See, oxidation state of A is going from 0 to plus 1. 0 to plus 1. So I would say this is the initial oxidation state of A. This is the final oxidation state of A. N factor of A would be equal to change in the oxidation state of A. Change in the oxidation state of A, which is final oxidation state of A minus the initial oxidation state of A. Take a mod of it and the value comes out to be 1. Right? This 1 is the change in the oxidation state for one atom of A. And over here I have only 1. Right? So the N factor of A in this reaction is nothing but it's 1. As simple as that. Right? Similarly, my dear students, if I write N factor of B, N factor of B, change in oxidation state of B, final minus initial. Final is minus 1, initial is 0, the change comes out to be 1. 1 is the change for one atom of B, and here I have only 1, so multiplying it with number of atoms, so N factor of B here also is 1. Okay, I hope this is clear. I hope this is clear to everyone. Let me take one more example with that. It will be properly clear to you. For example, I've got the reaction A2 plus B2. A2 plus B2 gives, for example, 2 times A positive plus 2 times B negative. Okay. Now, first of all, oxidation state here 0, 0. Here it is plus 1. Here it is minus 1. Right? Now, 0 to plus 1, increase, oxidation, so reducing agent. 0 to minus 1, decrease, reduction, so oxidizing agent. So, let's try to calculate N factor of A2 here first. N factor of A2. Get the change in oxidation state. N factor of A2. Get the change in oxidation state. What is the final oxidation state of A? That's plus 1. Initial oxidation state of A, that is 0. Change is coming out to be 1. 1 is the change in oxidation state for one atom of A, but here I have 2. So I'm multiplying it with 2. So its N factor automatically comes out to be 2. Right? Similarly, if I ask you to calculate N factor of B2, how do we get the N factor of B2? Final oxidation state of B, that's minus 1. Initial oxidation state 0. The value comes out to be 1. 1 is the change in the oxidation state for one atom of B, but I have here 2. So its N factor is nothing but its N factor is 2 here. Right? And if you got the N factors of A2 as well as B2, you can easily calculate their equivalent masses. How? Molecular mass divided by N factor. That's it. Am I clear with this? Am I clear with this? Let me know quickly in the chats. Am I clear with this? Perfect. All right, people. Now, let me tell you, there are some very important oxidizing agents which you need to know. Have you heard about KMnO4? It's a very strong oxidizing agent. It's a very strong oxidizing agent. This KMnO4. And this KMnO4, let me talk about some important things about this KMnO4. My dear students, in different mediums, KMnO4 shows different reactions. In different mediums, KMnO4 shows different reactions. Let me first of all tell you, in your acidic medium. In acidic medium, you will see KMnO4 getting converted into Mn di positive. In acidic medium. Let me write it over here. In acidic medium, you will see KMnO4 getting converted into what? Mn di positive. Okay? This is the first and the important point which you need to remember. KMnO4 getting converted into Mn di positive. In which medium? In acidic medium. Second medium is your neutral, or you can say slightly alkaline medium. Slightly alkaline. Slightly alkaline. In neutral or slightly alkaline medium, this KMnO4 gets converted into MnO2. It gets converted into MnO2. And let me tell you, in your strongly basic medium, in strongly alkaline medium, it gets converted into MnO4 dinegative. It gets converted into MnO4 dinegative. So these are, first of all, the three things which you need to know about KMnO4. In acidic medium, Mn dipositive. In neutral medium, MnO2. In strongly basic medium, MnO4 dinegative. Now, my dear students, think logically. Oxidation state of manganese here is +7. Oxidation state of manganese here is +2. Here the oxidation state of manganese is +4. Here the oxidation state of manganese is +6. Right? Now, in acidic medium, +7 to +2. KMnO4, +7 to +2. Right? Get the n factor of KMnO4 in acidic medium. Get the n factor of KMnO4 in acidic medium. +7 to +2. Calculate the change. Final minus initial. Final minus initial. Final is +2. Initial is +7. Mod is 5. So remember, n factor of KMnO4 in acidic medium is nothing but it's 5. N factor of KMnO4 in acidic medium is 5. Similarly, in neutral medium, +7 to +3. Change comes out to be 3. So n factor of KMnO4 in neutral medium is 3. And similarly, n factor here is going to be 1. So these are, first of all, the three important things which I would want every one of you to remember. N factor of KMnO4 in acidic medium 5. N factor of KMnO4 in neutral medium 3. N factor of KMnO4 in your strongly basic medium, that is 1. Even there was one question asked long back related to KMnO4 as well. What was that? That was the ratio of equivalent mass. Ratio of equivalent mass of KMnO4 in acidic, neutral, and strongly basic medium. Okay. Let me write here KMnO4. Let me write here KMnO4. Let me write here acidic medium. Let me write here neutral medium. Let me write here strongly alkaline medium. Okay. What is the n factor of KMnO4 in acidic medium? We know that already. That's 5. Here it is 3. Here it's 1. Okay. Here it's 1. This is basically, these are the n factors. Okay. If these are the n factors, what about their equivalent weights? Equivalent weight of KMnO4 in acidic medium will be molar mass divided by n factor, molar mass divided by n factor, molar mass divided by n factor. Now get the ratio of these equivalent masses. So this m, and this m gets cancelled out. So ratio comes out to be 1 by 5 is to 1 by 3 is to 1 by 1. Okay. Now you can slightly modify this ratio over here. See, what is the LCM of 5, 3 and 1? LCM of 5, 3 and 1 is 15. So I'm multiplying 15 here, I'm multiplying 15 here, and I'm multiplying 15 here. And when you multiply it, this is 5, 1, 5, 3. This comes out to be 3. This comes out to be 5. This comes out to be 15. So the ratio is coming out to be 3 is to 5 is to 15. This is the ratio of equivalent masses of KMnO4 in acidic, neutral, and strongly alkaline medium. Am I clear with this again? Similarly, there is something called as K2Cr2O7. You might have heard about it. K2Cr2O7. It's again a strong oxidizing agent. And remember, in acidic medium, it gets converted into Cr tripositive. Just this thing you have to remember. Your K2Cr2O7 in acidic medium gets converted into Cr tripositive. Now, my dear students, chromium, here is in +6 oxidation state. Here chromium is in +3 oxidation state. +6 to +3. If I ask you, what is the n factor of K2Cr2O7 here? +6 to +3. Calculate change. Final minus initial. The value comes out to be 3. 3 is the change for 1 atom of chromium, but here we have 2. So 3 2s are 6. So n factor of K2Cr2O7 in acidic medium is nothing but 6. Okay? It is 6. Perfect? It is 6. Now here only let me mention one more thing. Here only let me mention one more thing. What is that? There are some common reactions shown by your KMnO4 and K2Cr2O7. Some very common reactions shown by KMnO4 and K2Cr2O7. What are those? See, first of all, let me tell you, KMnO4 as well as K2Cr2O7. KMnO4 as well as K2Cr2O7 in acidic medium converts. Number one, Fe di positive into Fe tripositive. Fe di positive into Fe tripositive. Number two, it converts Sn di positive into Sn plus 4. It converts I negative into I2. It converts oxalate C2O4 dinegative into carbon dioxide. Number 5, converts H2O2 into O2. H2O2 into O2. H2S into sulfur. H2S into sulfur. Similarly, SO2 into SO4 dinegative. Right? This is what I'm talking about, your KMnO4 and K2Cr2O7. KMnO4, K2Cr2O7 in acidic medium converts Fe di positive into tripositive, Sn di positive into Sn plus 4. Now people, if you just remember this particular chart, you can easily note down the reactions as well. For example, let me write the first reaction. KMnO4 converts what? Fe di positive. In which medium? Acidic medium. Into what? Into Fe tripositive. And itself in acidic medium gets converted into Mn di positive. And with this you just have to write water as well. Okay? Perfect. Similarly, let's say here, KMnO4 converts Sn di positive. In which medium? Acidic medium. Into what? Sn plus 4. Itself gets converted into Mn di positive. And with this, you'll be writing water as well. Right? Similarly, KMnO4 converts I negative in acidic medium into I2. Itself gets converted into Mn di positive. And with this, you'll be writing water as well. Simple. Right? And I believe the rest of the reactions you can easily write. Perfect. Similarly, you can write the reactions of K2Cr2O7 as well, because K2Cr2O7 shows the same process. K2Cr2O7 shows the same process. For example, I have to write this reaction for K2Cr2O7. See, K2Cr2O7. It converts oxalate ion in acidic medium into carbon dioxide. Itself gets converted into Cr tripositive and just add water with it. That's all. Similarly, this reaction also you can write. Let's say K2Cr2O7 converts H2O2 in which medium? Acidic medium. Into what? Into O2. Itself gets converted into Cr tripositive, and with this you'll be writing water as well. Right? Similarly, you can write all the other reactions too. So my point here is just remember all this stuff. KMnO4 K2Cr2O7 converts what into what? That's it. That's all what I need from you. Nothing more. Okay? I believe it's clear. I believe it's clear. I believe it's clear. Let's have a look on some of the questions based on your n factor calculation. Let me see if you understood it or not. Can you tell me what is the n factor of I2 here in this reaction? N factor of I2 in this reaction. See, it's pretty much simple. Its oxidation state here is 0. Here the oxidation state of iodine is +5. So 0 to plus 5. 0 to plus 5. What do I need to calculate? I need to calculate n factor of I2 will be equal to 0 to plus 5. Calculate the change. Final minus initial. Final minus initial. The value comes out to be 5. 5 is the change for 1 iodine. Here I have 2. So 5 into 2 is equal to 10. N factor of I2 here in this reaction is 10. Okay. For example, I want to calculate n factor of IO3 negative as well. If I want to calculate n factor of IO3 negative, then I have to reverse the process like this. I have to reverse the process. Now I'll be calling this as initial, this as final. So final is 0 minus initial is plus 5, change is 5. 5 is the change for 1 atom. Here I've got only 1 atom. So 5 multiplied 1 is 5. So its n factor here is 5. Okay? Right? Sir, electrolyte deposition you did not share. Okay. I'll share that after the session in the Telegram. If not, just remind me once. If not, just remind me once. Okay? Perfect. Let's have a look on one more question then. For example, this is the question. What do you think is going to be the n factor of VO? What do you think? N factor of VO. Again, the same process you have to follow. What is the process exactly? Vanadium, its oxidation state here is plus 2. Vanadium here, its oxidation state is plus 5. Change in the oxidation state. Final minus initial. The change is 3. 3 is the change for 1 vanadium. I have 1 only, so its n factor is 3. What is the n factor of V2O5? Change. V2O5, reverse. Final minus initial. Final is plus 2. Initial is plus 5. The value comes out to be 3. 3 is the change for 1 vanadium. Here I have 2. So 3 into 2 is nothing but it is 6. So this is how you calculate n factors, and I believe it's clear. Okay, for example, this is the question. Let's say you have to calculate n factor of this particular species. Okay? Let's say you have to calculate n factor of Fe 0.940. How do we do it? Understand. What is the oxidation state of this iron? I've already shown you when we started the oxidation states. I've told you what is its oxidation state. It's plus 200 divided by 94. Plus 200 divided by 94. What about the oxidation state of iron here? It is nothing but plus 3. So this to this. Same process. Final oxidation state minus initial oxidation state gives you change in the oxidation state for 1 atom. But how many do we have? 0.94. So multiplying at the end with 0.94. Solve it and get the n factor of this particular species also in this reaction. I hope this is clear. Right? I hope this is clear to everyone. Perfect, guys? Now, my dear students, one thing. There are some species which show dual nature. Dual nature means in some reactions they'll be behaving like oxidizing agents. In some reactions, the same species will be behaving like reducing agent, like H2O2. H2O2 in some reaction behaves like oxidizing agent. In some of the other reaction, it behaves like the reducing agent, right? The three such common compounds, which in one of the reaction behaves oxidizing agent, one more reaction behaves reducing agent. They are your H2O2, HNO2, and FeSO4. Remember them. Now see, oxidation state of oxygen here is -1. Sometimes you will see this H2O2 getting converted into water, and sometimes you will see this H2O2 getting converted into oxygen. Okay? So sometimes from -1 to -2, sometimes from -1 to 0. And when it goes from -1 to -2, decrease means reduction, right? So oxidizing agent. Similarly, -1 to 0, increase in the oxidation state, oxidation, so reducing agent. And when it behaves like oxidizing agent, its n factor is 2. Here also its n factor is 2. You can check it out also. -1 to -2, change is 1. 1 is the change for one atom. I have 2, so its n factor here is 2. Similarly, minus 1 to 0, change 1. 1 is the change for 1. I have 2, so its n factor is 2. Right? These are the three cases which you have to remember. For example, FeSO4. Here iron is in plus 2 oxidation state. Plus 2 to 0, sometimes plus 2 to plus 3. Plus 2 to 0, decrease, reduction, oxidizing agent. Plus 2 to plus 3, increase, oxidation, so reducing agent. N factor, plus 2 to 0, change is 2. 2 is the change for 1 iron, I have 1. N factor is 2. Plus 2 to plus 3, change is 1. 1 is the change for 1 atom, I have 1. So its N factor is 1. Okay? So there are some substances which sometimes behave like oxidizing agent, sometimes behave like reducing agent. So remember this. Okay? Now similarly, guys, there is one more thing. Till now, I showed you only those oxidizing and reducing agents in which oxidation state of only one element was changing. Till now, I showed you only those oxidizing and reducing agents in which oxidation state of only one element was changing, and we were calculating change in the oxidation state of that element only. Okay, till now. But there are some compounds in which oxidation state of more than one element also changes. There are some elements in which oxidation state of more than one element changes. What do we do in those particular cases? See guys, for example, I've got a compound ABC. Let's say this is the compound ABC. Perfect. Let's say this ABC compound is participating in some reaction. It is participating in some reaction. And during the reaction, for example, oxidation state of A is increasing, oxidation state of B is also increasing, oxidation state of C is also increasing. Let's say I'm giving you a scenario. Let's say I've got a compound ABC. It is participating in some reaction, and in that reaction, oxidation state of A as well as B as well as C is increasing. How do we calculate N factor of this particular species? N factor of this particular species is nothing but it's going to be N1 plus N2 plus N3. Okay, N1 plus N2 plus N3. Let's say you have got a compound ABC. In some reaction, let's say oxidation state of A is decreasing, B is decreasing, as well as C is decreasing. Right? How do we calculate N factor of this species at that time? How do we calculate N factor of this species? It's again going to be N1 plus N2 plus N3 only. I'm directly giving you the tricks. I'm directly giving you the shortcuts. For example, you have got a compound AB. You have got a compound AB. Let's say in some reaction, oxidation state of A is increasing and oxidation state of B is decreasing. How do I calculate its N factor then? Its N factor is going to be mod of N1 minus N2. Just remember these three basic cases, and I'll show you its examples so that you'll get used to all this. Okay? Now, what kind of examples are here? Let's try to check. Understand this particular case. Guys, have a look. Iron here is in plus 2 oxidation state. Carbon here is in plus 3 oxidation state. Iron here is in plus 3 oxidation state. Carbon here is in plus 4 oxidation state. Now have a look. Plus 2 to plus 3, increase. Plus 3 to plus 4, again increase. Right? So can I say this is the compound in which oxidation state of more than one element is changing? And how it's changing? Oxidation state of iron as well as carbon, both is increasing. So whenever you see such kind of the compound in which oxidation state of two elements simultaneously increases, how do we calculate its N factor? It's going to be simply N1 plus N2. N1 plus N2. N1 plus 2 to plus 3. Plus 2 to plus 3. What is the change? 1. 1 is the change for one atom. I have only 1. So N1 value is 1 here. Plus 3 to plus 4. Plus 3 to plus 4. What is the change? 1. 1 is the change for 1. I have 2. So I got N2 value as well. Now tell me, N1 plus N2 makes it 3. So its N factor in this particular case is 3. N factor in this particular case is 3. Let me give you a few more examples like that. Oh, what did I do? Let me give you more examples here. Okay, have a look on this particular case. First of all, this copper Over here is in +1 oxidation state, sulfur is in -2 oxidation state. Copper here is in +2 oxidation state, sulfur here is in +4 oxidation state. Okay, now check it out. +1 to +2, increase in the oxidation state. -2 to +4, increase in the oxidation state. The oxidation state of two elements is simultaneously increasing. Right? So, how do I calculate its n factor? If oxidation state of two elements is simultaneously increasing, so it's going to be n1 plus n2. Now, we just have to calculate n1 and n2. Okay, guys, +1 to +2, change is 1. 1 is the change for one atom, I have 2. So, n1 value is 2. -2 to +4, change is 6. 6 is the change for 1, I have 1 only. So, n1 is 6 plus 2, makes it 8. Again, one simple question. Again, one simple question. For example, look at this particular case. Look at this particular case. These are all the questions which I'm showing you. Okay. Oxidation state of Bi here is +3, sulfur is -2. Right? Bi here is +5, sulfur is 0. Now check it out. +3 to +5. +3 to +5. +3 to +5. What will happen? +3 to +5. Increase. -2 to 0. Again increase. So, n factor of two species are increasing. So, it's going to be n1 plus n2. Right? Now, +3 to +5. The change is 2. 2 is the change for one atom. I have 2. 2 2s are 4. So, n1 value is 4. -2 to 0. Change is 2. 2 3s are 6. So, n2 value is 6. 6 plus 4 makes it nothing but 10. Okay? Makes it 10. I hope this is clear. Let's have a look on this particular case. See, iron here is in +3 oxidation state, sulfur is in -2. Iron here is in +2, sulfur is in +4. See, iron's oxidation state is decreasing, sulfur's oxidation state is increasing. So, oxidation state of one element is increasing, another one decreasing. One increasing, other one decreasing. So, how do I calculate its n factor? One increasing, other one decreasing. So, it's mod of n1 minus n2. Now, +3 to +2, change is 1. 1 is the change for 1, I have 2. So, n1 value is 2. -2 to +4. -2 to +4. Calculate the change. Final minus initial. The change is 6. 6 is the change for 1. I have 3. So 6 3s are 18. So it comes out to be 18 minus 2. That comes out to be 16. So I would say n factor of this particular species here is 16. Is this clear? Perfect. Now similarly, guys, there are some species which undergo disproportionation. There are some species which undergo disproportionation. How do we calculate their n factors? N factor for those n factors for those species which undergo disproportionation. Let's have a look. N factor for those species which undergo disproportionation. For example, I've got a reaction like this. A2 plus B2. Or just a second. Let's say I've got the reaction like this. A2 gives Let's say I've got the reaction like A2 gives A positive plus A negative. A2 gives A positive plus A negative. Now I'm asking you just one thing. What is the oxidation state of A here? You'll say 0. Oxidation state of A here +1. Oxidation state of A here -1. 0 to +1. Increase in the oxidation state. 0 to -1. Decrease in the oxidation state. Can I say oxidation state of the same element is simultaneously increasing as well as decreasing? Whenever you see such a species in which oxidation state of same element simultaneously increases as well as decreases, right? We say that particular species undergoes disproportionation. And whenever a species undergoes disproportionation, its n factor is nothing but n1, n2 divided by n1 plus n2. Now, we have to calculate n1 and n2. 0 to +1. Change is 1. 1 is the change for 1. I have 2. So, n1 is 2. 0 to -1. Change is 1. 1 is the change for 1. I have 2. So, n2 is again 2. So, it's going to be n1 multiplied by n2 divided by n1 plus n2. The value comes out to be 1. So, n factor of this A2 over here is nothing but 1. Right? I hope I'm clear with this. Right? Similarly, guys, let's say I'm taking one more reaction. Let's say you have got a reaction like this. Br2 gives Br negative plus BrO3 negative. Let's say this is the reaction. Br2 gives Br negative plus BrO3 negative. Now, if you think logically, oxidation state of bromine here is 0. Oxidation state of bromine here is -1. Oxidation state of bromine here is +5. Okay? Now, check it out. 0 to -1, decrease. 0 to +5, increase. So, oxidation state of same element is simultaneously increasing as well as decreasing. I would say this particular species is undergoing disproportionation. And whenever a species undergoes disproportionation, how do we calculate its n factor? It's nothing but n1, n2 divided by n1 plus n2. Right? Now, get the value of n1. 0 to -1. Change is 1. 1 is the change for one atom. I have 2. So, n1 is equal to 2. 0 to +5. Change is 5. 5 is the change for 1. I have 2. So, 5 2s are 10. n2 is 10. So, it is going to be 10 multiplied by 2 divided by 10 plus 2. The value is 20 divided by 12. So, 5 by 3. So, n factor of Br2 in this reaction is nothing but 5 by 3. Okay. Similarly, there was one question asked in AIMS long back related to the same. What was that question? The question was like this. You were given with the reaction H2O2. It gives H2O plus O2. You were supposed to calculate equivalent mass of H2O2 in the reaction. Can you solve this right now? Can you solve this right now quickly? Can you solve this right now quickly? What is going to be the n factor of H2O2 first of all? Check it out. N factor of H2O2. See guys, oxygen here is in -1 oxidation state, here oxygen is in -2, here oxygen is in 0. -1 to -2, decrease. -1 to 0, increase. So oxidation state of same element is simultaneously increasing as well as decreasing. So its n factor is going to be, again n1 n2 divided by what? Divided by n1 plus n2. Now, -1 to -2. Change is 1. 1 is the change for 1. I have 2. So n1 value is 2. -1 to 0. Change is 1. 1 is the change for 1. I have 2. So n2 value is also 2. So it's nothing but 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. Right? N factor of H2O2 is 1. Therefore, equivalent mass of H2O2 is equal to molar mass of H2O2. That's 34 grams. Divided by n factor. That's 1. So equivalent mass of H2O2 in this particular reaction is going to be 34 grams. Right? I hope this is clear. I hope this is clear to everyone. Now guys, there is one more topic. There is one more topic here in the redox reaction. What is that? Your balancing. That's your balancing of redox reactions. That is balancing of your redox reactions. Okay, balancing of your redox reaction. Balancing of your redox reactions. See, there are a lot of ways by means of which you can balance the reaction, but you don't have to remember all of them. You do not have to remember all of them. You just have to remember one of the methods of balancing the reaction. That's sufficient for you, right? And I'll show you the easiest way of balancing the reactions. Now see guys, first of all, let me show you how do we balance the reactions in acidic medium. How do we balance the reaction in acidic medium? Have a look. Understand and remember. Understand and remember. For example, I've got the reaction like this. MnO4 negative plus Fe di positive. It gives Fe tri positive plus Mn di positive. This is your reaction. For example, I want to balance this reaction in acidic medium. Understand what I'll be doing. First of all, I'll try to calculate n factor of MnO4 negative. See, plus 7 to plus 2, its n factor is 5. Right? Plus 2 to plus 3, its n factor is 1. My first step is the calculation of n factors. My first step is to calculate the n factor of reactants. Okay? Once we get the n factor of reactants, then we'll crisscross these reactants. This 1, I'll make the coefficient here. This 5, I'll make the coefficient here. Perfect. First of all, get the n factor of reactants. Second point, crisscross the n factors. Crisscross the n factors. After this, balance all the atoms except hydrogen, oxygen. Balance all the atoms except hydrogen, oxygen. Except hydrogen, oxygen, you need to balance all the atoms. See, 1 manganese, 5 iron, and 5 iron. Balance all the atoms except hydrogen, oxygen. Next is going to be balance oxygen with the help of water. How exactly? How many oxygen on this side? 4. How many oxygen on this side? None. So right side is oxygen deficient. How many oxygen deficiencies on right side? 4 oxygen deficiencies. So just add 4 water molecules on that side, which is oxygen deficient. Now, after balancing oxygen, balance hydrogen. Balance hydrogen. With the help of what? With the help of H positives. How many hydrogens on this side? No hydrogen. How many hydrogens on this side? 8. So this side is hydrogen deficient. So add 8 H positives on this side. Now it's a balanced chemical equation. That's it. Right? That's it. Perfect. Let me give you one more example so that it becomes properly very clear to you. See guys. For example, I've got Cr2O7 di negative plus, let's say I've got Sn di positive. For example, it gives Cr tri positive. And with this you have got Sn plus 4. Let's say. First of all, get the n factors of reactants. The oxidation state here is plus 6 to plus 3 is 3. Change is 3. 3 is the change for 1. I have 2. So its n factor is 6. Plus 2 to plus 4. Its n factor is 2. Right? First step. Crisscross the n factors. Make this 2 as the coefficient here. Make this 6 as the coefficient here. Now, balance all the atoms except hydrogen, oxygen. 4 chromium. So 4 chromium. 6 tin. So 6 tin. Now, oxygen. 14 oxygen. No oxygen. So 14 water molecules on this side. 28 hydrogen on this side. So 28 H positives on this side. The reaction is balanced. Am I clear with this? Am I clear with this, people? Quick. Am I clear with this? Right? So this was balancing in which medium? Balancing in acidic medium. Now let's have a look. Let's try to solve one question in basic medium as well. Let's try to balance one reaction in basic medium as well. Yeah. For example, this is one reaction which we have to balance in basic medium. In basic medium, there is only one change. In basic medium, there is only one change. The change is, first of all, you have to get the n factors of reactants. You know that already. Then we are supposed to crisscross. Done. After crisscrossing, balance all the atoms except hydrogen, oxygen. Okay. After that, you have to balance negative charge with the help of OH negatives. Then balance oxygen with the help of water molecules. Balance oxygen with the help of water molecules. For example, have a look on this particular question. Cl2 plus IO3 negative gives this plus this. In basic medium, we have to balance. First of all, oxidation state of chlorine here is 0. Here it is -1. 0 to -1. Change is 1. 1 is the change for 1. I have 2. So its n factor is 2. See, this is +5 here. +5 to +7. Change is 2. So its n factor is also 2. So I got the n factors of the reactants. 2 and 2. If you got the n factors, just crisscross them. So 2 here, 2 here. Crisscross the n factors as well. Now balance all the atoms except hydrogen, oxygen. So 4 chlorine on this side, this should be 4 chlorine. 2 iodine on this side, this should be 2 iodine on this side. Okay? Perfect. Now after this, we have balanced all the atoms except hydrogen, oxygen. Now we have to balance the negative charge. We have to balance the negative charge. My dear students, here you do not have any negative charge. This molecule carries a negative charge, -1. So one molecule carries -1, so 2 will carry -2. So basically on left side, the charge is -2. On left side, the charge is -2. On right side, this chlorine has got -1, so 4 chlorine will have -4. IO4, one molecule carries -1, so 2 molecules carries -2. -4, -2 carries -6. So on left side, the charge is -2, right side charge is -6. Which side is negative charge deficient? Left side or right side? I'll say left side is negative charge deficient. How much negative charge deficiency is there? There is 4 negative charge deficiency. So on this side, which side is negative charge deficient? I'll add 4 OH negatives to balance the negative charge. To balance the negative charge. Now, what is the next one? Next is we have to balance oxygen. We have to balance oxygen. That's pretty much simple. How many oxygen on this side? 4. 4 plus 6 is 10. Here 4 2s are 8. 10 oxygen on this side, 8 oxygen on this side. So which side is oxygen deficient? Right side. Add 2 water molecules on this side to balance oxygen. The reaction is balanced. The reaction is balanced. So this is how we do the balancing of reactions as well. If I'm clear, let me know once in the chats. Let me know once in the chats. Okay. Guys, there is one more topic left here, that is redox titration. But titration is nowadays not in the syllabus of the NEET. Okay? It is nowadays not in the syllabus of the NEET. Well, in JEE, they can ask those questions. But if you still want to have a look on the titration, then I would suggest one of my sessions. You can open the playlist. You can open this playlist. And when you open this playlist, here is a redox reaction. And over here, that titration topic is I've discussed in detail, okay? But you can avoid that also. You can avoid this topic also. Okay? You can avoid this topic also. But if you still want to have a look, then it's taught here. You can check it out. Basically, this topic is nowadays asked in your JEE mains, not in your NEET syllabus. Okay, so you can avoid, you can skip the titration topic. Got it? All right, people. So whatever things we have discussed till now, is every single thing clear? That's what concept of equivalence I'm talking about. That's titration part. This one, which is currently happening. Okay, so tell me whatever things we have discussed till now, is every single thing clear? I think this is perfect. And I think, guys, we won't be able to complete all the chapters in the today's session. I have to schedule part 2 for this. Okay? I will have to schedule part 2 for this marathon. Okay? So it is impossible to complete this because I have taught you all the things in detail. So I will have to schedule part 2 for physical chemistry. Let me check the schedule when we can have the part 2. Just a second. Let me check the schedule. Part 2 of this physical chemistry we can have after 4 days. Okay? After 4 days, we'll have its part 2. Yes, this redox part is completed. Redox part is completed. Okay, tell me once, with all the things, whatever things I've discussed in the today's session, are things clear? Are all the things clear? Oh. Yeah? Yes, these sessions are going to be enough. They are enough. They are enough. They are enough. So the remaining chapters include your atomic, equilibrium, and thermo. We'll do them in the next part. Okay? Let's end the session here only because I don't want to rush in those chapters also. I can complete them, but it will be like just the overview. I don't want to do that. I do not want to do that. Okay? I want to complete those chapters in detail as well. So that's why I'm telling you to, we'll schedule part 2 of this. All right? So honestly, tell me whether whatever things we have discussed, are all the things clear? Honestly, you can tell me. You guys also take rest and just revise whatever things I've discussed, just revise it. Okay? Just revise it, people. Just revise it. Ion electron method is not needed. You have balanced the reaction with oxidation number. That's enough. And do let me know in the comment section of this video whether you got all the concepts. And I would want a comment from every single one. Whosoever watched today's video, I would want one comment from everyone whether you got all the concepts or not. From everyone watching me right now. Okay, in the comment section of this video. And part 2 will be there after 4 days, in which I'll be discussing atomic, your equilibrium, and your thermo part. Okay? Because if I do those chapters now, it will be like completely rushing. I do not want to rush them. I want to teach them in detail. So let's schedule part 2 here. Okay? With this, I'll be taking a leave. You take care. God bless you all. But I would be expecting a comment from every single one related to whether you got each and every concept or not. That is a kind of satisfaction as a teacher. Okay?